Welcome to the RQI Circuit 2026. So this week we're here in Hangzhou, China, at Westlake University. I'm very grateful to Hongguang Liu for hosting me here for the week. It was a very good week so far. So this RQI Circuit is a series of local conferences that is being organized by the ISRQI, this International Society for Relativistic Quantum Information. So basically, if you're interested in the society and the research being done here and at the other places, feel free to go to the website, which is isrqi.net. And this little link here on the right allows you to register or log in. So if you're interested in the community, want to hear about the events and all of these things, feel free to access this website and register to the society. So without further ado, let me give it to Ioannis Soranidis, who is the local organizer here, and who will say a few words as the opening remarks. Thank you so much for organizing.
Thank you very much, Rick, and thank you for making all of this possible here today. I'm very glad to actually host this event here at Westlake University. This is the first time that we have an RQI event in mainland China, so that's very good for us. And the organization committee is basically Professor Hongguang Liu, me, and his master's student, Chong Zhang. He will start his PhD soon, actually. And I don't think I need to say anything more. We can actually start with the talks. And I would like to urge the speakers to remain within these lines, because this is the region that will be shown in the broadcasting. And the talk format will be 30 minutes. You can have 25 minutes plus 5 minutes of question. If you don't have time for questions, that's all right. But as long as you remain within the 30 minutes, it will be fine. So yeah, we can start. You can use your own computer if you want. So you can send me the talks, whatever you want. It's fine. Yeah. So let's invite the first speaker, Shan-Ming Ruan.
Should I just start?
Yeah, so let's start the RQI circuit here in Hangzhou. So the first speaker is Shan-Ming Ruan, and he will talk to us about finite black hole interior in quantum gravity. The floor is yours.
Good morning, everyone. So it's a great pleasure to be here to visit this fancy university again. So today I will talk about some recent work, like the work we've done over the years. So basically the idea is like we're trying to explore like the understanding the black hole interior in quantum gravity. Since the organizer told me like there should be a broader, like it should be a talk for a broad audience, but I'm not sure like how broad it is. So I basically give you some like introduction about the work, all the motivations, it's like the background. And then the rest of the part, I will focus on some work we've done over the last several years to understand like how the finiteness of the black hole interior, and also some recent work about the black hole singularity. But if there's some terminology or some terms you are not familiar with that, you can just raise your hand and ask the question. I can explain more in details. All right. So this is basically just outline for this 30 minutes talk. All right. So the main point is like like in the black hole thermodynamics, there's a fancy, like the very fundamental things about the black hole entropy, like the Bacon-Sand entropy. So it's like A over 4G. So one point, like over the development, we know that this beautiful formula provide a lot of hint about like quantum gravity, especially if you look at this length scale. It's like quite a big number. So in some sense, this tells us this big entropy actually implies the black hole state should be corresponding to like a lot of microstates which form this black hole we see in the geometry. And a more important thing, like this is just an area law. So this entropy is different from like the general size or like the general system we consider, which the entropy is just a proportion to the size rather than the area of the system. So this area law also implies the very fundamental like principle we believe now for quantum gravity, like the holographic principle. So this is proposed by Chunhao and Lenny Susskind, probably 30 years ago. All right. So based on this. Of course. Yeah, based on this holographic principle and also especially the string theory, Marcina proposed the ADS-70 correspondence. So roughly speaking, like the idea here is like this ADS-70 correspondence in the string theory actually realize this holographic principle for gravity. So roughly, you can see the statement basically is about like this book geometry, like inside the spacetime. This is the ADS plus one book spacetime, and which is due to the theory live on the boundary. So in this case, I just give you two examples. So in this left-hand side, we have like a one-side black hole with a black hole in the book side. And on the boundary, this is due to like a thermal state, which is live on the d-dimensional safety. And more importantly, you can even consider like a left and right, the two-sided ADS black hole. So this will give you another duality, which is due to like the two-sided state on the boundary. It's like the same fadable. All right. So one of like the things we follow in the last 20 years is about like all the inspired is by this similar formula, which is called the RD formula. So the idea is also very similar to the black hole entropy. So here, this is a holographic formula for the interim entropy. You can see the left-hand side is the interim entropy for the boundary system. Let's say we consider some CFT or some field theory, live on like the boundary without gravity. So we consider subregion A. And then you can easily see like this subregion A defines some density metric, like a mixed state. And that's very natural to see like if you want to measure like the entanglement, the quantum entanglement between the system and its complementary. So in this example, it's like entanglement between the A and B system. So this kind of like very like a simple quantum signature for the entanglement in the quantum system. And then the duality based on the ADS-FT or the RD formula-based state. In the book, you should be able to also calculate the entanglement for the system A. And then it turns out the result is also very simple, and it's surprisingly simple. So it's just given by the area over the 4G. The difference here is like this area is area for the minimal surface leaving the book. So the minimal surface, like you can just find like an infinity surface connecting or like closed by the system A. But then you can just minimize to get like the minimal one, which give you precisely the entanglement. So now, the leading order, the entropy for the subregion A between the A and B system. So this is kind of like a very beautiful formula, which is also very similar to the entropy, similar to the black hole entropy we just mentioned before from the Bacon-Sand entropy. So based on this, like I just give you like a very simple example. So why this entropy formula or the RD formula actually help us to understand better about the quantum feature about the gravity side. So this is just a simple example proposed also by Marcina before. So the idea here is like if we just consider this particular book geometry, which is like the two-sided ADS black hole. And sometimes this is just like eternal black hole because it never evaporates. So this is why people sometimes call this eternal ADS black hole. So you can see like according to the ADS safety correspondence, this should be a field theory or the field state live on this left and right boundary, and precisely given by the conjecture proposed by Marcina. So the dual for this particular book geometry is on the boundary is given by the so-called semi-double state. So there's several hints why we can see this is like the duality we need. For example, as I mentioned before, if we just look at instead just a one-sided ADS black hole. So let's just consider just the right or left side. And then you can naturally see like the boundary duality for this state should be given some mixed state. So this is, you can see just if I trace out the half of the system, like the left or right, this duality, this state just corresponds to the precise thermal ensemble you see on the boundary. So this is what is better. And then this two-side state is more like like the quantum purification. You just make a copy between the left and the right, and then make a purified state. So the simplest one to purify the mixed state is just given by the simplified double. And then you can also see like this is why the left state and the right state, like the left geometry and the right geometry, have this asymmetry between the left and right-hand side. So this is exactly the symmetry we see on the simplified double because they are just like a copy for each other. All right, and then based on this duality, we can see now that's a very simple way to interpret what is the entropy we see before, like the black entropy. So for example, now we can consider the black entropy we defined before for this area 4G corresponding to the area for this horizon. It's actually the entanglement entropy, the holographic entanglement entropy, which between the left CFT and the right CFT. So you can see if you just take this simplified double state for the two-sided ADS black hole, this left and right is entangled by some entanglement entropy. And then in this book side, this entanglement entropy will be exactly given by the black hole entropy we see before, like the A/4G. So this is based on the RD formula. The difference is just like now, the minimum surface between the left and the right is precisely given by the black hole horizon. So this is why based on this RD formula, we can claim like the RD formula now becomes kind of not just a cosine entropy for the black hole system, it's also microcanonical entropy for like the boundary left and right states. All right. So this is just like one simple thing we like the one simple examples why the entanglement entropy or the RD formula help us to understand like the quantum feature about the gravity. So I want to say like there's more important lessons we get over the last 20 years. It's about the space-time itself. So we generally like according to the general relativity, we take the space-time itself as a background, like the curved background. But from these studies over the last 20 years, what we get here is more like the space-time, or the most important lessons we have here is like the space-time itself is not so fundamental as we thought before. So in that sense, you can see it's even like kind of be considered as the emergence from like the entanglement, like the quantum entanglement. So this is simplified double is also the simplest example. Let's see, instead of considering like some entangled state between the left and the right, I just pick up like some product state between the left CFT and the right CFT. So this will be like give you some also product spacetime. So you see like the ADS spacetime on the left and the right should be just decoupled. They are like no entanglement or like no touch to each other. But if we just increase the temperature to increase the entanglement between the left and the right system, let's say we just increase temperature to get some entangled like the simplified double state. So in the book side, what do we do is by increasing this entanglement, what do we get is like this two-sided ADS black hole. So the spacetime will be like smoothly connected from the left to the right. So in that sense, you can see why we have this like a smooth connected geometry which entangle the left and right is because we increase the entanglement between the left and right. So in that sense, you can see if I just decrease the entanglement, what do we get is a spacetime which is decoupled to each other. So this is why, in that sense, you can see this black hole interior geometry or this connected geometry we see, this smooth book spacetime is actually a result of the quantum entanglement. Because if we don't have entanglement, then what do we see is just kind of a trivial geometry. All right. So based on these examples, like all these lessons, that's a kind of a simple slogan given by Marcena and Susskind probably 10 years ago. So it's stated as like ER equals EPR. So the ER here is referred to as like the Einstein-Rosen bridge. So roughly see, like I can see, this is just kind of like a simple Lorentzian wormhole, which connecting left and the right. So this like this geometry is like connecting from the left to the right by the Lorentzian wormhole. And sometimes I don't really distinguish like at least in this example, the Lorentzian wormhole is just referred to as the Einstein-Rosen bridge. It's like the bridge connecting the left and right by the wormhole geometry. And then on the right-hand side of the slogan is given by the EPR. So this is just like the entangled EPR pairs. So it's referred to as the entanglement. So basically, this is not really some equations to state some precise equation. It's kind of like slogan to advertise. Like the idea behind this slogan is like this entanglement, quantum entanglement for the bounded state or even for the bulk states is actually a result of the wormhole which connecting left and right universe. Or can even consider this a more general to see the more big pictures here is like the entanglement, the gravity understanding about the entanglement, quantum entanglement is a result of the wormhole geometry in the spacetime. All right. So this is just like the warm-up for the work, the development over the last 2 decades. So here I want to talk about more like our recent work about like try to understand the black hole geometry, like especially the interior geometry. So it's like the geometry behind the Einstein-Rosen bridge, like this wormhole geometry in the quantum gravity. Of course, we don't really have like a concrete example to realize what is quantum gravity. So in the next step, what I do is a more like a simplest way. So it's like based on this ADS safety cost bonus, because from the boundary side, it actually provide a very like a quantum theory. So if we can understand the black hole geometry from the boundary viewpoint, like the safety side, it's actually provide a way to understand the book geometry from the quantum viewpoint. But here I want to mention is like instead of considering like the general ADS safety, like the large limit, what we want to consider here more is like we try to fix the finite n system. So generally, it's not precise like what is the relation between the boundary size n and the book parameter. So roughly speaking, you can say like the n here is just kind of a dimension for the hash space we want to consider, like the black hole macro state. And then it's given by the e to the s. So this is the book parameter, parameterize the total size of the hash space. Because we roughly believe like this black hole entropy should measure the dimension of the hash space. And then you can see like what do we do here is like we take the entropy or the G Newton to be finite. So this is why the total size of the system should be finite. And then we can include some finite n corrections to the description for the book geometry. And then this is basically like the goal we want to do to like see like if we're including these finite n corrections, what we can get from the book geometry side. All right. So the first thing I mentioned here is like it's about like the black hole real, the size of black hole real, and associated with like the holographic complexity, some kind of like a proposed duality between the book geometry and the boundary quantity, which is called like the complexity. We'll explain later. All right. So this is still like the simple examples I just mentioned before. So now let's see like the simplest way to understand the black hole geometry inside the black hole interior is just like you can just draw time slice. So this time slice actually prove the black hole interior because this Einstein-Rosen bridge inside between the left and the right horizon is just the black hole interior. So if we can understand this geometry, it actually help us to understand what is the book geometry, the black hole interior geometry. Turns out this time slice is actually very simple. So in the sense, if we just consider like the time slice from t to 0, and then we're involving this time slice to see the time evolution. As a result, the time evolution of this state or this time slice present a very simple geometry behavior. It's just like at like a larger time, you can see this size of that black hole interior is almost just grows linearly. So it's like a very simple, precise like a description for the black hole interior geometry. So this linear growth is actually capture the growth of the black hole real. So this is a simple geometry fact about the black hole real, about the wormhole. But in another side, you can see if we want to understand this black hole geometry, which is behind the horizon, as I mentioned before, time entropy or the holographic time entropy provide a very powerful way to understand the book geometry. But you can find in this example, this quantum entanglement actually is not enough to prove this black hole real. Or this long-term black hole real. The reason is like this geometry increase is actually could extend from order 1 time to infinite time. So this is a very long time, like linear growth. But you know, like I mentioned before, the time entropy is given by some minimal area. And then you can also consider similar the time evolution for the holographic time entropy. But as a result of the minimization, you will find this book side, the area should be like reach to the maximum value very quickly. So this also corresponds to the normalization for the boundary system. We do expect that the entropy should increase and then reach the semi-equilibrium value. So in this case, you will find because this is normalization, you will find this holographic time entropy actually is not enough to prove this like infinite time long like linear growth for the black hole real. So this is why it's proposed by Lenny-Susskind, like the time entropy is not really enough to prove this, like, or to understand this black hole real geometry, especially this like a simple long-term linear growth. So instead, he proposed like just a simple boundary duality to capture this linear growth from the boundary side. So this is given by people define the complexity. So the simplest example of the conjecture is given by the complexity equals volume conjecture. The idea is like this volume we see connecting the left and right. So in this case, you will find that there are also infinity slice you can draw from the left to right. And then in this case, we do like the maximization rather than minimization because the minimum one just gives you 0. You can always push this to be null to get like the 0 volume. So the maximum volume you can get here is actually give you the simplest linear growth, which capture the growth of the wormhole or the black hole real. And then this duality or the conjecture-based state, this maximum volume is due to a boundary quantity, which is called a complexity. So this is some like the geometry or some like fundamental concept associated with like a computational or computing. I guess most audience or probably some audience are familiar with this. I will give you some other explanation later. All right, so in the simplest case, from the boundary side, what do we call complexity? Roughly speaking, you can see like in this example, let's just consider some quantum circuit. We have some like the fundamental or some initial state. And then I try to prepare some target state. For example, like the thermostat or the ground state of the CFT. So we can just use like the fundamental gate we have to like involve this initial state to the end to get the target state we want to get. And then in this, all the possible circuit we can build on this fundamental gate. You can find that's a different infinity gate you can use, infinity circuit you can find. But the one we are interested in is more like the simplest one or the minimal one. So it means we can consider like the circuit complexity. And then by definition, this is roughly speaking, it's just given by the minimum number of the gates we use to prepare this like the circuit, which is given the target and also given the reference. Okay, so this is basically tells us if you have this physical state at the end, this target state, how hard it is or how complex it is to prepare for a very fundamental like product state. All right, so this is just like another example why we want to consider like this quantum circuit in the ADS book side or the gravity side. So this is like given by the so-called ADS mirror correspondence. So the mirror is like the multi-scale entanglement rhythm-analytic ansatz. So this is one of the simplest or the powerful like the tensor network. So in this case, you can see like the mirror just prepare like start from this product MPS state, and then with using this entanglement and rescaling gate, we can finally prepare some state given by the ground state of the CFT. And then this is just the simplest quantum circuit you can use to prepare this like CFT ground state. But then if you believe like the ADS CFT or just apply the ADS CFT correspondence in the bulk side, at the beginning you can see like this state doesn't have an entanglement. So in the bulk, it doesn't really due to any geometry or the bulk spacetime. It's just given by some point. And then at the end, what do we get is the CFT ground state. So if you like apply the ADS CFT, what do we see in the bulk side is just given by the ADS spacetime. So this is implied if you just apply this circuit in the bulk spacetime, what you will get is actually the emergence of the spacetime itself. You just start from a point and finally emerge the whole ADS bulk spacetime. So this is why it's kind of templating to try to understand this tensor network or even like the general quantum circuit in the ADS CFT correspondence. So this is like another example, which probably more well known because this is like the slogan for the von Qubit calibration. So this is actually the heavy code, which is also particular like a tensor network. So roughly see like the points like you can just consider the ADS geometry like this cylinder, and then you just pick up a time slice. So the powerful thing or the amazing thing here is like this time slice, actually you can fill by this discrete tensor network. Of course, this is just one example like given by the heavy code. There are also some other examples, for example, like the random tensor network. Yeah, but the point here is like this time slice for the ADS book span actually is filled by the tensor network we consider to prepare this like the state for the boundary side. So you can ask if you want to know how complex for this state it is. Roughly speaking, you can see like what number I use to prepare this, or the number of the tensor I use to prepare the state or this network is actually just given by the volume for this time slice. So this is why at the beginning we just mentioned like this is why Lenny conjectured like this maximum volume for the ADS time slice actually corresponding to like the circuit complexity we use to build the state. Okay, and this is just like the simplest example, and more like generally. Like based on the work I did like several years ago with my supervisor, Rob Myers, and also Berlin, Cyrus, and Sabrina, we have like the more general proposal for the holographic complexity, which probe the black hole real. So like we call this complexity anything proposal. Roughly, like the idea is like we just consider like some, for example, in this left-hand side case, we consider some time slice, and then no matter what the measure you use to measure this time slice, it actually probe the black hole real. And then you can even consider some codimensional zero subregion and put some like some geometry measures, which is a different invariant, will be enough. And then in that sense, no matter what measure you use here, as long as this is some extreme quantities, you can find all these infinite measures give you like the simplest linear growth, which capture the growth of the black hole real. So this is why we also consider like all these infinite measures is kind of candidate for the holographic complexity in the bulk side. All right, but here I just mentioned like this linear growth for the black hole real is kind of like understand or the conjecture to be due to the increase the linear growth for the complexity. But if you really look at this quantity from the bulk viewpoint and from the quantum circuit viewpoint, you can find if I consider some like the time evolution for the boundary state or the target state, the states will also have like the complexity for this state also depends on time. And then if I consider some like the general chaotic system, the evolution for the complexity is very simple. roughly you can see like the general evolution for this quantum circuit or the circuit complexity is just given by this plot. For long term, it's just presented this in linear growth. And then it's just reached until the exponential time, which is given by the dimension of the Hall space. So this, because at this time scale, you can believe like all the circuit will explore like all the possible state in the Hall space. So this is why finally you just reach some like the state which give you the maximum or the most complex complexity. And then this is why we expect at the late time, this complexity should just reach the plateau. So this is also like, roughly you can see just because it's constrained by the size of the Hall space. We have just a finite dimensional Hall space. So this is why we can always explore all the possible states and to see there's always some state give you the maximum entropy. So maximum complexity. So this is why we do believe like this complexity should stop increasing at some time and reach the long-term plateau. But if you just consider this same time evolution from the both side, what we get is kind of like a very different picture. As I mentioned before, there's a kind of match between the linear growth because what we see is there's long-term like linear growth for the wormhole. And also on the boundary, there's a long-term linear growth for this complexity. But the difference in here is like in the book side, what we consider is like a single geometry in the book. So roughly saying like in the Euclidean path integral, what we do here is like we just consider G Newton of the entropy to infinity to make this saddle point to be like the only dominant saddle point. So this is why you can just consider one single classical spacetime. So this is just given by like if you want to match the story or match the calculation, it's actually just a match for the larger N system. Doesn't really count like the finite N quantum corrections. And as a result, you can see that's kind of a paradox. We do see like this linear growth, we start from finite time to the infinity, which is like a match with the boundary side. But this book evolution could be involved, not just like a finite expansion long time. It's actually just go to the infinity. So in that sense, you can see, you can always find inside the book geometry, this black hole horizon, inside the black hole horizon. What we see is not just like a linear growth like wormhole. Finally, you can find the wormhole give you infinity volume. Because you can find in this case, I can always make the time slice reach this constant radius slice in the book. And then this constant radius slice inside the horizon is actually a constant time slice. And this time slice actually give you the infinity volume. So this is the final slice we see, which give you the linear growth, but it can also give you the infinity volume. But as I mentioned before, for the general finite dimensional quantum system, we do believe like this complexity, or by definition, this quantum complexity should be bounded from above. So this is why it should be like a long-term plateau of some like transition time. So that's kind of like a paradox between the book story and the boundary calculation or boundary expectation. But as I mentioned before, like the key point here is like this book calculation or this single geometry is a result for the larger limit or like for the G Newton to zero limit. So this is why it just gives you the contribution for a single set of point. So the point here is like we want to see this infinity black hole integral in the book. We do see this infinity black hole integral in the book, but this is just a geometry fact about the black hole spacetime. But from the boundary, the Hall space should be bounded. That's a finite dimensional Hall space. So this is why it's kind of like a contradiction between some calculations. But the whole point is just because if we want to consider the black hole macro state, as I mentioned before, if we consider the entropy to be finite with keeping the G Newton to be small, but still like non-zero, in this sense, this dimension of the Hall space for the black hole is roughly given by e to the s of the black hole entropy. And then like the most general, like all the spectrum we do expect for the black hole quantum state in the quantum gravity is kind of like this spectrum. They are very like a chaotic and random like state in the corresponding to the black hole macro state. But there will still be like a finite dimensional like Hall space, which corresponding to like this e to the s, which is like precisely the dimension of the black hole macro state. But why we can understand this black hole spectrum? Of course, if we know like the Hamiltonian to do like a full quantum gravity, like if we know like the Hamiltonian for the boundary theory, you can also consider like what the aging value for this or the aging spectrum for this Hamiltonian. But in the quantum gravity, we don't really have this powerful way to understand like the quantum fact about the gravity side. But that's one very important hint or like the input we have for the quantum gravity. It's like we believe like the black hole system is not like a general quantum system. It's actually very special. The point I want to stress here is like the black hole we consider in the book or in the quantum gravity is actually due to not just a normal quantum system. It's given by some chaotic system in the boundary. Or even in the book, if you believe like the quantum gravity in the book, it's also mean like the quantum gravity state due to the black hole state should be just given by some quantum chaotic system like the random metric theory. But based on this like a strong input, we can still like we don't really like fully fix the spectrum for the black hole max state, but still provide a lot of lessons about like the quantum spectrum for the discrete spectrum for this quantum black hole in the book. Yeah, the point here is like the quantum chaotic system, like the general quantum chaotic system, is like believed to be typically described by this like the random metric theory. So this is mean like the random metric universalities. So this is like if you consider, basically the statement is like if you consider some general like a quantum system, chaotic system, this spectrum is like universally described by the random metric theory. All right, so this is basically like the powerful way we can understand like some features about the quantum gravity, like especially this spectrum statics. Okay, maybe I just skip this. And one point, our one realization over the last 10 years is about like a very simple time model in the quantum gravity. It's given by this 2D jet gravity. And then you can find, based on this work, you can find the 2D jet gravity is actually equivalent to the ensemble for the random metric theory. So this is realized the example I mentioned before. We can use like the random metric universality to understand like the bulk geometry, especially like in 2D, this is like a precise duality between the boundary random metric theory and the bulk geometry. So the corresponding you can also calculate by using this Euclidean path integral. And then, for example, if you calculate the partition function, this is just corresponding to E Velt, this like a partition function for the random metric, which given by some like the ensemble we consider due to the different potential in the book. All right. So what we do here is like a very similar calculation by which keep the finite n system. So as I mentioned before, we have some infinity like a volume. And we do see this linear growth from the geometry side. But now let's say I want to keep the n to be finite. And more generally, I want to include quantum corrections. So what we do here is like instead of considering just some geometry quantities, we involve like we including this, we define some like the operator associated with this like the complexity or the volume we do like in the book. And then we try to evaluate this general function e to the minus alpha c for this symmetrical state. And then this equation value actually give you the quantum corrections or provide some quantum corrections. So the thing here is like based on like this decomposition, what do we need actually to calculate this quantity is very simple. It's just quantum mechanics calculations or some random metric calculations. So that's like two ingredients given by the spectrum correlation, which is determined by the system we consider. And then there's a metric element determining what is the operator we consider for this quantity. So the good thing here is like we have a very strong holographic input which could decide rather than just the whole quantity, but it's actually determining what is the time evolution. So the point is like if we keep the genome to be finite, this linear growth actually constrains the possible way we can write for the metric element. So actually constrain what is the metric element we should consider. And more importantly, in order to include quantum corrections, we believe like this is should be given by some quantum chaotic system. So based on the random metric universality, we can find even we don't know what is the spectrum for this spectrum correlation, but actually we can fix the universal part for this spectrum correlation by using the random metric theory. So this is why we can fix actually a lot of information about this decomposition and to get the calculation for the time evolution. And then finally, the result we have here is like no matter what the measure we used before for this complexity of black hole real, the time evolution turns out kind of like a universal. It's presented just like the linear growth as we expected before, but because we're including or we keep the finite n corrections or finite genome corrections, we can find this linear growth finally will be just like reach the maximum value at the time e to the s. The s is like the black entropy as we expected, and then go to the constant plateau. So the point I want to mention here is like this is the result we believe like because what we consider from the fundamental side is just a finite and a discrete black hole spectrum. So this discrete finite black hole max state actually in the book imply the book spectrum we can consider is not like infinity black hole interior. There are always like a finite black hole interior in the quantum gravity. So this is why you can support like a finite dimensional space. And more importantly, this is universal evolution because the system we consider not just a simple quantum system, it's actually a quantum chaotic system. So for example, in this case, we're not just including quantum corrections to cancel the classical linear growth. The important thing here is like the system we consider presents the level repulsion, which is the fundamental feature for the quantum chaotic system. And then based on this level repulsion, we can prove like the evolution at the late time is always reach like the plateau given by the constants. I think due to the time constraint, probably I just skipped the part about the singularity because this is still like some work I'm doing with my students. Maybe I just skip to the summary. So the key point here is like, the study we want to do here is like, we know like the Einstein gravity theory tells us like the space-time geometry is just like the gravity theory. So this is the whole point for the Einstein gravity theory. But if we want to do quantum gravity, the simplest way or the things we can understand better now is about this Euclidean passing integral for the gravitational passing integral. So the point here is like in the Euclidean gravitational passing integral, what do we consider not just a single geometry? So for example, if you apply the set point approximation, what you get is like the leading order is given by the classical geometry. But there's still some high order quantum corrections, which is like other set point given by this high genius geometry. So this is generally called like a Euclidean wormhole or space-time wormhole. So in this like random metric calculations, what we do is like we include in some corrections which correspond this like high genius geometry or this Euclidean wormhole geometry, and then we organize this Euclidean wormhole geometry in terms of like random metric predictions. So this is like a result. We can include in some quantum corrections in the quantum gravity in the gravity calculations, and more importantly, you can see in the classical geometry side, the classical signature for the geometry is actually not really like a faithful representation for the quantum gravity. For example, if we want to see this infinity black hole integral, or even want to see the singularity, or even the horizon itself, it's actually just a result of this Lagrangian limit. We take the n to infinity and g n to 0, and then all this geometry feature for the classical geometry could emerge. But instead, in the quantum gravity, if you consider finite n with including all these corrections, what you see is actually different from the classical prediction from the both sides. I think this is probably the whole message I want to advertise here. All right, I think I should stop here. Thanks for your attention.
Quick questions.
Thanks for your talk. Under the complexity equals anything proposal, did you find that the time scale where the plateau begins depends significantly on the observables you choose?
Not really. Yeah, this is the point. Yeah, exactly. So the things like we try to see the transition from the linear growth to the plateau here. But turns out like the transition time roughly is more sensitive to like the two-point function or the spectrum correlation. So this is given by the system we consider. Rather than like so the information about the anything or the measure we use, like the complexity of anything, is determined by this metric element. So this is C operator. So it depends on like what's the measure you want to consider. But the transition time is more sensitive to this spectrum correlation. So this is based on what the quantum system we consider. So in that sense, like if you consider the same geometry in the book with like fixing the spectrum correlation, the transition time you see roughly is the same order or almost the same. For example, in the sine kernel, this is just given by the so-called Heisenberg time. It's like e to the s over 2 with some coefficients.
So it's not the case that some probes can see the quantum effect sooner than others?
Exactly, yeah. So this is more about like we included the Euclidean wormhole, and this Euclidean wormhole in the book precisely cancels the linear growth in the book geometry. So it's not so sensitive to the measure. It's because yeah. Yeah, the measure tells you more information about like, for example, the growth rate here, and also what are the constants you can consider here, and also details around the transition. But roughly the whole universal structure more sensitive to like, this is why we can do this calculation for the general like measures rather than like fixing one particular measure like a volume.
Thank you.
Thanks for the nice talk. Look, I have a question. If you will include some corrections to JAR, what will happen?
To what?
Because you consider this in the framework of JAR, if I understand, your geometry is determined by ADS as a solution to JAR. So if your JAR action gets corrections from EFT or from whatever.
You mean the G-Newton?
Yes.
Yeah. So you mean like so basically like we consider the G-Newton to be like the classical value, But what we try to do is like So I call like a finite genome because like the parameter we use in the boundary set actually is capital N. So it's given by the e to the s. So this is why what we do here is like we keep the correction from e to the minus s. But in the quantum gravity, because the genome is very small, so roughly at the leading order, you can say that this is just quantum correction. You can even just drop out. But things like this is a late time illusion. So at the time scale compete with this. So this is why these two scales could be like to give you some finite corrections. But we don't really consider we don't try to find effective description for genome itself. We just like we keep the genome at the leading order and then keep this expansion, try to track the subleading corrections.
I see. Thank you.
I actually had a similar question along these lines. So if you consider some quantum corrections to that, supposedly some higher order curvature corrections, and you have a solution based on that, you expect some kind of regular geometry. And once you have this regular geometry, which is devoid of singularities, you expect some problematic behavior close to the extremal limit. And I've seen some work on that, and I see some divergences emerge just based on entanglement entropy. So I don't know how this framework of complexity will be modified in this case.
Yeah, I think like in the end, I don't really have time to talk about the singularity. This is like a similar story. The things like we want to understand like there's a, but also like this is different from like we try to do quantum correction for the bulk geometry. So the whole point is like we want to do the Euclidean path integral. So the geometry itself is not really fundamental. It's just a set of points. So you substitute like one single set of point, single geometry, and this corresponds to just focus on one set of point corrections. But the result we get from the boundary point is more like we sum over all the set points, especially in the singularity case, even if sum over the set point is not enough, you also want to do the path integral to sum over all the fluctuation around the single set point. But in that sense, we actually lose the description for the geometry. So this is why like we see like we want to do here is more like we understand this, we try to understand what is the bulk geometry from boundary side. But from the boundary side, you don't really like we don't really write down a metric. It's like we use some like observer, for example, the coordinate function from the boundary to describe what is the geometry we can see or we can predict from for the bulk side.
Thank you. So if there are no more questions, we should thank the speaker one more time. So the next speaker is Chunhao from Hongguang University, and he will talk to us about geometric realization of stress tensor, deformed field theory. The floor is yours.
So, is the pointer? The pointers don't work.
You should use this for changing the slides.
But how to turn page? I see. So good morning, everyone. Welcome to thanks to the organizer to give me opportunity to give a talk here. And today I will talk about the geometrical realization of the stress tensor deformed field theory. And I'm Song Hee, and this work is based on the service paper collaboration with my postdoc, Jose, and Tommaso, and also from Italy, and Robert Taddeo from Italy, and also my former colleague from Jilin University, Ouyang Hao. And also with my postdoc, Li and Ouyang Hao and Sun Yuan, and my two excellent students, PhD students, Li Yunzhe and Xie Yunfei, and also from Xu Lixin from Dalian University. And the outline of this talk will be the following. First, I will introduce the basic background and personal motivation. And the second part, I will focus on how to geometric realization of the two-dimensional stress tensor deformation, typically the TT bar deform and root TT bar deform. And the third part, we try to extend to the higher dimensional case to how to emerge in gravity from stress tensor deform field theory in generic dimensional spacetime. And finally, I will give a summary and perspective. So the basic motivation is try to understand the nature of the gravity, or typically probably the quantum gravity. And we know there is a very nice property for the quantum gravity. Typically for the, as Shan-Ming said, present, there is a so-called the holographic nature of the quantum gravity is proposed, originally proposed by the Tohoff and Susskind. And exact realization to this holographic property realized by the Marcella, very famous paper. Typically, the typical example is ADS2, ADS5 type 2B string theory correspond to the n equal 4 super Yang-Mills 4-dimensional super Yang-Mills theory. There are various aspects of this holography in terms of this so-called the ADS safety correspondence, and also some slight extension for the long ADS safety correspondence, like long ADS2 and JT gravity and SYK model. And all this story is higher dimensional gravity correspond to the lower dimensional field theory on the conformal boundary. And here we try to this is typically for so-called the open-closed duality in terms of this worksheet description. And the exact target space realization of this open-closed duality is realized by this standard example. But here I just try to propose some alternative way to understand the gravity. And here in this talk, we are mainly focused on the same dimension of the space-time, start from the field theory to the emerging gravity. Probably it's an alternative way to understand gravity, or we propose some new duality probability, and we propose some sort of experiment to try to go beyond the holography. So in this talk, we don't have nothing to do with the holography. We just start from the main point is start from the field theory, same dimensional field theory to emerging gravity. So this is the central point. And the basic background, can we go beyond the holography? Is it possible to find some to derive same dimensional space-time gravity from field theory, or you just try to propose some new try to semi-classically or classically to unify the field theory and gravitational theory. And we propose some possible candidate, which is so-called the stress tensor, energy moment tensor induced deformation. And we will start from the this idea is originally proposed by this Sakharov a long time ago, 1967. And at that time, he proposed some just start from the very simple, naive, a thought experiment. You can just start from the same dimensional space-time. Initially, the space-time is flat, and here we just put some matter. We put some matter on the space-time, and the matter will be slightly deformed the space-time. So once the matter put in the space-time, and the space-time will be slightly curved. So how to emerge the gravity? So once the space-time to be curved, so in that sense, the gravitational degree of freedom will be slightly emerged. How can we realize this process? And we propose some very simple sort of experiment, like one scalar field theory. We just put one scalar field theory, start from just the pure field theory, and start from this space-time. And this scalar theory will be induced, so-called the energy moment tensor, typically for two-dimensional case. And later you can see we can extend to the higher dimensional case. And so once this scalar series, single safety or TB a free scalar, and they put this matter here, and the gravitational degree of freedom will be slightly emerged. We will show how can we show this experiment, this sort of experiment to be realized in terms of this start from the field theory to derive the gravity in the same space-time. So in that sense, the gravity here and the field theory here stay on the same space-time. And so we try to the typically example for the two-dimensional case. There are very famous two examples. One is the so-called the TD bar deform and the root TD bar deform. TD bar deform is once you define the two-dimensional field theory, and the induced energy moment potential will can be written as a so-called can be induced from the field theory or from seed theory. So this is the so-called T mu mu here, and you can introduce some so-called the typical deformation from the determinant T or square root T TD bar deform. But for the TD bar deform, which is so-called proposed by the Smirnov and Zamalojkov, and they introduced in the field theory side is so-called the TT and minus theta. Theta is a trace part of this energy moment tensor. And you can recently the people try to extend this notion to be root TD bar case. And the TD bar case is in two-dimensional case usually is called to be irrelevant deformation. But for the root TD bar case is associated with so-called marginal deformation. So this is the two typical energy moment tensor deformation. So what is the deformation? How can we do this deformation field theory? And you can start from start from the seed theory. This is the seed theory action. This is the deformed action for this guy, and you just solve this classical equation. Just try to solve this deformed field theory, and you can. There are various ways to show how can you do the stress tensor deformation. And we just show very simple typical example. Just we start from the free scalar theory, and you do this. We just solve this previously. We solve this equation of motion. We solve this equation, and to try to find the deformed action. Typically for the one scalar theory, and one scalar will be deformed after the TD bar deform, and this guy will be the resulting deformed theory will become to the lam go to action, which is the so-called the lam three-dimensional flat space, and the phi here is correspond to the Oringer phi, and you can identify two worksheet and tau and sigma to be coordinate to be the target space. Just to fix the gauge fix and to do the proper gauge fixing, and then you can write down this deformed theory to be a non-local lam go to action, which is a three-dimensional non-critical string theory. Forget about any to consider the quantum aspect of this non-critical string theory, and you can look at this. This start from this local theory with TD bar deform, and which one the resulting theory become to the non-local, which is the so-called lam go to standard lam go to action. So this is since this two-dimensional case, TD bar is associated with irrelevant deformation. In that sense, from this typical example to show that you can start from the local theory to be highly non-local. Since the TD bar deform is a IR theory and is irrelevant, so in that sense, the deformed theory is to be in a UA to be highly non-local theory. So how can we see this effect? So start from the since here we start from the free scalar theory and the deformed theory to be highly non-local. How can we from this non-local theory? Classically, we can look at this deformed theory with have some effect associated with non-local effect. This in a classical gravity, we also saw some non-local effect. We will show how can you look at. So here, start from this very intuitive lessons from the TD body form, and you can start from the lamp go-to action, and then just introduce the auxiliary field like lambda AB here, and just integrate over the phi field here or chi x field. So integrate over this, just use the equation of motion for the x field, and the resulting theory to be gravitational theory. You see that the gravitational action is contained some high derivative term associated with the gravitational degree freedom, and also the cosmology constant. So from this very simple exercise to show that you can start from the C theory is a free scalar with a TT bar-like deformation typically in two-dimensional case, and we found the C theory with resulting theories to be C theory coupled with gravity. This is very, very simple example to show how can we emerge gravity. So this is very typical example, and here we try to extend this just observe this correspondence or some so-called classical duality, and we just slightly generalize this understanding, and also start from the C theory with a TT bar deformation, and we can find that with after the TT bar deform or TT bar-like deform or stress tensor deform, and the stress tensor and the final resulting theory to be found is correspond to the C theory coupled with gravity. So in that sense, from this very simple example, we try to extend this philosophy to be, you just start from the QFT, and the QFT will be induce some energy moment tensor, and we put some composed operator to deform this theory. So in that sense, start from the C theory with a TD bar or stress tensor deformation, and the resulting theory to be a gravitational theory. So in that sense, we just do the geometrical realization. Typically, in the previous example, we showed this very simple example start from the free scalar theory plus TT bar deform. We have a geometrical realization, and the resulting gravitational theory to be C theory coupled with gravity. So here we, in the second part, I will focus on how can we start from the so-called the TT bar deform or root TT bar deform, typically in a two-dimensional case to do the geometrical realization. And so you see that this is this story is very simple. You just start from the very simple exercise. Start from the C theory. A C theory coupled with the so-called the massive gravity, which is proposed by the Tony, and typically the two-dimensional case. This is the starting theory or seed theory. Seed theory can be once you this is a massive so-called the massive gravity. The massive gravity can be choose two different components. One is associated with dynamic degree freedom, and gamma mu correspond to the reference background. And all this background, all the two typical background can be written as a verbum with a different verbum. And so here the two-dimensional massive gravity can be simply just write down the very simple ghost-free gravitational massive degree freedom. And we solve this equation of motion for this dynamic background for the E mu mu, which is associated with the dynamic background. G mu associated with the G mu mu, and here you just put back obtain the solution of this equation of motion and put back to the original so-called the massive gravity coupled with the seed theory, and you can see that the resulting theory in the classical level, and you can see the flow equation, exact flow equation associated with the deformed. This associated with the lambda. Lambda is associated with the deformation parameter. Here we saw this lambda is associated with the TD bar deform. So you just pull back and take an onshare of this gravity, And you can see that the deformed action is the deformed TD bar deformed flow equation exact the same as with seed theory coupled with massive gravity action. So in that sense, on the classical level, you can exactly check start from this massive gravity exactly correspond to the TD bar deformed field theory. So this is very simple exercise to show that to convince you that once you do the start from the seed theory, you do the TD bar deform, and you can obtain some so-called massive gravity. Just free scalar or just a seed theory coupled with massive gravity. How can we extend to the TD bar and the root TD bar? Because typically the in two-dimensional case, there are two very simple stress tensor deformation. One is the TD bar, or other is the root TD bar. Root TD bar corresponds to the marginal deformation. And here you just follow up this same logic philosophy. You just start from the free scalar theory or simple seed theory. You couple with so-called massive gravity. But what type of the massive gravity to be? And we have to choose this dynamic background and also reference background. And typically you just use a try by error to write down some Lorentz invariant term, and then you can find the very simple example. And here I don't show some detail, but basically the philosophy is the same. Here we introduce a so-called the lambda associated with the TD bar deform and root TD bar associated with the gamma. And once you do, you just take this dynamic background, just take a solution of the dynamic background, and pull back this solution to the gravitational action here, and you can find the deformed action to be satisfy this so-called this associated with lambda is associated with the root TD bar deform, and gamma is associated with the root TD bar deformation. And we can exactly show that this two type of this deformation. One is a TD bar deform. There is the other is a root TD bar deform. The two type of the deformation is commutative. So in that sense, the resulting theory to be or correspond to the so-called the seed theory coupled with minimal coupled with gravitational theory, massive gravitational theory, and this is the two typical example. We can simplify this process and to write down this simplified massive gravitational background. The alpha here associated with the TD bar deform, and the gamma here also associated. The gamma here is correspond to the root TD bar deformation. So this is very simple in two-dimensional case. You see that we start from the seed theory coupled with some to do this two type of this stress tensor deformation. You can find the resulting theory to be classically correspond to the gravitational theory. So this is very simple exercise to try to convince you. And here we just show very simple example for free scalar. You just still start from the free scalar and the seed theory, and the free scalar coupled with massive gravity here, and you can exactly check this resulting theory. Just pull back the E star mu A here correspond to the solution of this dynamic background. So resulting theory here is highly non-local, also so-called the non-critical string, three-dimensional non-critical string, Lam-Goldus string, classical Lam-Goldus string. And here gamma goes to zero limit. Gamma correspond to the root TD bar, and the gamma goes to zero exactly correspond to the standard Lam-Goldus action. So in that sense, we can exactly go back to the previous slide, previous example. And here, this is a typical example to show that you start from the seed theory, just start from field theory, and you just do this TD bar or root TD bar deformation, whatever type of this stress tensor deformation, you can exactly find some so-called the gravitational theory. So this is the central claim of this series work. And so there is some, but previously we showed some classical deformation, and how this process of philosophy can be extended to the quantum version. And here we just do some very simple observation, and there are some insights from the von Neumann algebra. For typically we start from the field theory, which is the so-called there is low semi-finite choice. Typically the QFT typically for the free scalar theory, and satisfy the set theory, satisfy the type 3 von Neumann algebra. Once you introduce typically for you introduce some so-called TT bar deformation. TT bar deformation parameter is laterally introduce some laterally cut off. In that sense, we for example previously we obtained the so-called the Lamb-Goto action. The Lamb-Goto action is highly non-local, and in that sense you can in the Hilbert space you can construct the finite finite choice. So in that sense, the von Neumann algebra should be from type 3 to be type 2, and also in that sense in the gravitational side, we expected the set theory plus some TT bar deform correspond to the set theory coupled with gravity. Once you gravitational degree freedom to be emerged, and so we can introduce so-called the finite semi-finite choice if we believe the quantum gravity to be here standard. So in that sense, there is low type 3 after the TT bar deform. There is low type 3 divergent entropy. So in that sense, this is very strong quantum aspect, quantum version insight, and to convince you that the deformed theory should be satisfied the type 2 von Neumann algebra. There is a finite choice. So this is very central sign point. Here we just show during the last 10 minutes. So I just introduced some how can emergent gravity start from the stress tensor deformation. Typically, you can ask. Previously, we start from the two-dimensional free set theory, but you see that you can emerge in the two-dimensional gravity. But the two-dimensional gravity there is low gravitational degree freedom, just only one scalar field degree freedom. So how can we extend? How can convince you for arbitrary dimensional space-time? How can realize this? Standard gravitational theory like a GR. And here we just start from the gravitational, we know the Einstein gravity. Well, you can start from Einstein gravity coupled with the minimal coupled with the so-called matter field. And you just do the gravitational positive integral. If you trust the gravitational should be, we can do this we can do this some in terms of this saddle point approximation to try to read out the gravitation to do the gravitational path integral. And here we have to take a typical saddle point, for example, G star, and also you can consider the gravitational space-time to be arbitrary topology of this gravitational background. And so typically we pick up the simple gravitational degree freedom, and we just solve this equation of motion, which is here we just focus on the very simple. In principle, we can't to do the gravitational path integral. Here we just do the saddle point approximation and nearby this GR or Einstein gravity. We just start from the GR and then we solve this equation of motion, and we can find you can find this resulting gravitational theory can be realized some so-called the deformed theory. This deformed theory is correspond to the some so-called seed theory plus some gravitational the gravitational degree freedom will be goes to be the TT bar deformed or TT bar like or stress tensor deformed degree freedom. So in this sense, and once you do the start point approximation to respect to the G mu mu, and you can find you can rewriting this gravitational saddle point just the gravitational degree just to do the gravitational path integral, and the resulting theory to be a field theory with some stress tensor deformation, and the resulting theory, the set theory is to be G alpha star, and with the matter field of psi, And the left hand, the second part of this turn will be just only composed by this G mu mu star and also induced stress tensor deformation. And this operator, and you can exactly check this one to be. This is a systematic way to write down how can we start from the set theory to be the gravitational theory to be set theory plus some stress tensor deformation. And so this we just check this philosophy in terms of this in terms of the two-dimensional case. And in two-dimensional case, we know this massive gravity effective action, and we can write down this G mu mu star is just like R mu mu star plus some stress tensor deformation. And you can exactly check this. Our philosophy exactly reproduce this so-called the two-dimensional TT bar deformation. So this is very simple example. And last 5 minutes, I will just show very concrete example. Typically, we start from the so-called the linearized Einstein gravity. This is a very standard linearized Einstein gravity, lambda to be vanished. And we just do the gauge fixing, and then you can find this gravitational, perturbably resolve this Einstein equation. And you can find that H mu mu star to be writing as some composed operator, T mu mu, and etc. So in that sense, this linearized Einstein gravity can be written as you just start from set theory coupled with deformed by this such type of this stress tensor deformation. So this is very, very simple example to show that this start from the free mass QFT and deformed by this composed operator, but this operator is not only stress tensor deformation, just only in some typical type of this stress tensor deformation. And you can write classically, you just start from the free scalar theory, and you introduce such type of this stress tensor deformation, and redefine the metric field. You can find this classically. You can start from the free scalar and couple with some so-called this. The second term is correspond to the linearized Einstein gravity. So this is very simple example. And here I just due to the time limit, and I just try to convince you how can we, because previously we just show this classical level, but how can we imagine linearized Einstein gravity semi-classically? So this is very simple example, and you just start from the free scalar and deformed by this stress tensor deformation, and you just do the path integral for this such type of the quantum field theory. This is purely all the ingredient is a quantum field theory. This is a quantum field theory, and deformed by this by this stress tensor deformation. But this stress tensor is induced by this seed theory. So you just totally to do this gravitational heat color expansion for this seed theory, and you can find this because there is a 2-point function for the energy moment tensor, and you can naturally emerge some curvature terms. But there are many divergent pieces. For example, this UV divergent piece associated with a capital lambda, and you just do the quantum field theory calculation, and you just start from the set theory, and we just do this one loop calculation for this deformation, and you find that this deformation terms associated with many UV divergent pieces, for example, lambda to 6 and etc. And finally, you just do the regularization and to do the standard quantum field theory approach to read out. This is a set theory, and a set theory coupled with some so-called the linearized Einstein gravity. And the coefficient here is small r 2 square over 2 lambda is correspond to the G Newton constant. So exactly at the quantum level, we just start from this free scalar, or you can extend to the Maxwell theory, and from Fermionic theory, you can also write down like the similar form. So we just do. we just do the very simple minimal subtraction in terms of the quantum field theory approach, and forget about this divergent pieces. Divergent pieces can systematically to removed by in terms of this regularization, and you can find this resulting theory to be seed theory coupled with so-called the minimal linearized Einstein gravity. So in that sense, we semi-classically to exact go back to the linearized Einstein gravity, and we just so there is a very simple example too. So here we introduce so-called the T bar T, and there introduce some so-called corner, and the corner here is just some the TT exchange the operator. The propagators to be some so-called the gravitational degree freedom. It's similar like a ghost in the field theory. We do the BRST quantization, and so we can naturally in the 1pi level we can exactly emerge in the classical 1pi level, and we can write down this the effective action for the propagator. So this is a very simple mechanism to understand how can we emerge in the same dimensional space-time gravity. So I will, due to the time, I will stop here. So thanks for your attention.
Are there any questions?
I can ask another question. So, I mean, it's very interesting that you obtain, after TT bar deformation, there is really a type 2 algebra. So it's really because you start with a scalar, for example, scalar field theory. After TT bar deformation, then there will be emerging diffeomorphism constraint, which makes it to be type 2, right? Then,
Yes.
Yeah. So, I mean, this is done in 2D, if I understand.
Yes.
Correctly. Okay. So,
but this is just a very simple insight to in terms of the von Neumann algebra or algebraic quantum field theory on the point of view, and because here we, as we said, that we start from the, for example, we start from the seed theory. This is QFT, and once you do the TT bar default, TT bar or root TT bar default, and you can obtain some resulting theory to be long critical string theory, long local critical string theory, three-dimensional space-time flat. Target space is flat three-dimensional space-time. So laterally, you don't forget about the conformal anomaly on the worksheet, etc. Laterally, this should be finite because laterally you have to introduce some so-called the cutoff scale associated with lambda. And in that sense, laterally, every observable quantum should be finite in the resulting theory. But that is very preliminary insight. It's not a concrete proof. It's just evidence.
Okay, thanks.
Any other questions? If not, let's thank the speaker once again.
Thank you.
And now we'll move on to the career development talk. So Hongguang Liu will give the career development talk with useful information about people that want to come to China to do their PhD, their undergraduate, postdocs, and relevant informations. And later on, I will continue with my experience as a postdoc here, as an international postdoc here. Hongguang, you can start.
Okay. Okay, so check. So this doesn't work. Oh, okay. Okay, so it's a great pleasure to host this RQI circuit at Westlake. So I'll present the career pathways at both Westlake, mainly at Westlake University, but also mention the RQI-related things in China. So in this talk, as Ioannis already mentioned, I'll give you some introduction to all the training programs at Westlake University. Contains both undergraduate, some summer research opportunities for undergraduate, which can somehow lead to the PhD program. And also I introduce our postdoc programs and also a special program that in principle can lead you to the tenure track position. So I'll mainly talk about, for example, where you can enter, so who you can work with, the larger groups here at Westlake, also at China, and what support we'll have and how to apply. Yeah, so I made a map, an interactive map that give you some hints that what will be the RQI. Sorry, let me do this. What are the RQI groups in China? This will be available on our website. So it's so you can click, for example, Hangzhou. Now it's our RQI circuit host. I listed some people. I mean, it's not a complete list. We'll expand that. But if we want to find some groups in China, you can just go to this map. And also our website. And also for Beijing, for example, we have Shan-Ming listed here. Yeah. You can find all the information you want. So let's continue. Yes. And now, I mean, you can see that there are already many places doing traditional RQI and also the expanded, more broader RQI things, including quantum information and quantum gravity, also holographic things. And they also start to have groups working on quantum reference frames and, of course, analog and quantum simulations related to the RQI. So it's still expanding, so we'll keep updating this map view. And if you really want to find some collaborators, you want to go to some groups in China, you can check. Yes, and now go to our university. So we are Westlake. You can already see this is our beautiful campus. And we are a very new university, founded initially launched in 2015, and the university was officially established in 2018, and we are mainly focused on fundamental and frontier research. There is no art, unfortunately. So we have very good research-led graduate training. That's the thing. And the university by design is a small university. That's the main, I would say, the main characteristics of the university. So in total, I think we finally will have around 400 faculties. Compared to very big universities, it's already a very small number. And the physics department actually has around 20 people. I mean, in many universities, this is not a very small number, but compared to many big universities, it's really a small number. Yeah. And of course, we are international and interdisciplinary. International in the sense that English is our working language inside the university. This is very rare in Chinese universities. Here, I I mean, concerning RQI-related things, there are mainly two institutes. One is the Institute for Theoretical Science, which is I based on. There are also School of Science, where physics department are there. And this Institute for Theoretical Science is basically mathematics and theoretical physics. But physics, so we are somehow, if you want to collaborate with physics department and also mathematics department, such that we have interdisciplinary environment, and we have more collaboration with mathematicians if you want. And this is good for theoretical physics study. And the training environment is quite international, and we have all the courses taught in English, and we have if you are a PhD student, we have the standard supervisor and also a graduate study committee, and also we have many seminars and conferences and also international exchange. So concerning my lab, so we are actually a quantum gravity lab. So we work on background independent no probability quantum gravity, RQG, spin forms, asymptoticity, and related things. We are also working in black holes and information, which are traditional RQI related. We have singularity study, or study information paradox, gravitational entanglements. And we also have mathematical physics and QFT. It's mainly about algebraic or constructive quantum field theory, also topological quantum field theory. And finally, it's no probability method and simulation, like randomization group, and many lattice and Monte Carlo method. Also, we have quantum simulation, and especially quantum simulation of quantum gravity models. And currently, we have 2 PhD students, 5 postdocs. 3 of them are long-term visitors, and Ioannis and Idris, who will come in the next year, are formal postdocs here. And we have also several visiting students. So I would say we are a very international group. From the people you can see, we have international PhD students, we have Chinese PhD students, of course, and we have many postdocs, which are foreigners, and they all come from different places over the world, and we work together. In a very good atmosphere. I think Ioannis and Sepiti probably will introduce later on. And we also have some other peoples. These are some peoples from the physics department and also chemistry department. So I can point out some peoples, for example, Professor Yan Zheng, a student from postdoc from his group will also present something about how to use entropy to characterize quantum many-body system and how to do this simulation. Also Wei Zhu, who work on fuzzy sphere, which are closely related, and they also use entanglement. And these are quantum information condensed matter physics, if you want. And also Wen Jieji, who just joined Westlake this year. She was originally from a faculty at Perimeter, and he also studied quantum matter system, topological field theory, and holography. Yeah. And we also have astronomy, like studying gravitational astrophysics and black holes, led by the chief professor Shu Demao. And also we have neutrino and dark matter experiments. Yeah. So I would say, I mean, the university encourage the collaboration between different groups, and we do have some collaboration with these groups. And now go to the real information probably people are interested in. So these are the undergraduate. We do have international undergraduate program. So for international applicants, actually you need to apply through a common APP, and all the most of the courses are taught in English, except some Chinese culture courses. So you and also you have the Chinese language course, of course, yeah. But in principle, you don't need to know Chinese. You can just apply, and we provide very good environment and also very good scholarships. Probably, I mean, the most interesting part is, of course, PhD. So we offer fully funded PhD program. There is a tuition fee, but actually all the tuition fee will be waived finally. And you'll get a fellowship and scholarship. around 85K per year, which is relatively good. And compare especially the price here for the other things here, because, for example, you have an on-campus single room in a 2-bedroom apartment. This is what you will get. This is the bedroom. And you also have a common room. And the price is actually 2,000 per academic year. It's not per month, it's per year. And actually, I can give you an estimation about the meals. So if you eat inside the university canteen, we have several canteens. They offer both Chinese food and Western food. And actually, it's 20 per meal. So you can calculate what you spent. Yeah. And also, we have very nice university environment. Probably Ioannis will tell you more about this. So for the application, so international students will go to this international route. I mean, it's basically very similar to the Chinese route. I'll tell you a little bit the difference later on. So to apply, you must have either a bachelor degree or master degree. The difference is that if you have a bachelor degree, you will enter the 5 years track, like the state's thing. But if you have a master degree, you will save 1 year. You don't need to go to this 5 years track, you have 4-year track. 1 year more compared to most of the European system, but you still save 1 year compared to the state system. And moreover, you have the possibility to graduate earlier if you really want, and you have a good achievement. I would like to mention that to enter the university, I mean, it's not irrelevant it's irrelevant to the application, but if you really want to go to this 4 years entrance, you must get your official degree before you start your study. Yeah. Okay. And this is the timing for the application. Please remind me the time. So this is the timing for the application. So for domestic students, you can already start to apply 1 year, exactly 1 year before. So the deadline for the application is around September, the year before you start your master, you start your PD. For international students, we have 2 rounds. One round, the deadline is around January. Another round, the deadline is around the end of March. And for these 2 rounds, one important thing is the deadline is always 10 a.m. Beijing time. So this is very important because there are some people, they think the deadline, for example, is the end of March. They use their time zone to calculate. Then they pass the deadline. They missed the deadline. So it's not so good. So be very careful to check what is real deadline. And after that, after each round, we'll have an interview. So if you enter the physics track, it's just the interview. There's no test, there's no exam. But if you want to enter the mathematics PhD program, there will also be an exam. You need to first pass the exam and then enter the interview. Okay, and usually the semester will start at September. Yeah. And that's where I mentioned that before the September, you must get your official degree. That's the rule by the Minister of Education. We don't, Otherwise, I mean, if you are a master, you don't suppose you didn't get your degree, then you will enter the bachelor track. That's the thing. Okay. I mean, before you come here for a PhD, you can consider our short-term programs. There are several different short-term programs. The official ones provided by the university is this summer research internship and also international summer school. And they also have their individual applications that's open to all the international students. So a typical duration is like 4 to 6 weeks during summer. And usually the application is start from the April until June for each year. You apply this and we'll give you an offer. If we admit you, you can come here to do your summer research or attend this international summer school. So we'll cover your local expenses. Flight tickets, you need to ask us. Yeah. And there are also visiting student track, which you can directly contact the supervisor you are interested. And just email, for example, just email us will tell you whether we have free slots. Yeah. There are also many scholarships and financial aid. But remember, all the PD program is fully funded. The scholarship is really a bonus for you. It's extra money usually. There are many different scholarships and many different financial aid systems. And also we have donation-funded awards. If you receive that, you get more money. Yeah. But the objective is just to let students focus on study, and you don't need to really think, how can I earn money if I don't have enough money? Yeah. Another important thing is, of course, postdoc positions. So postdoc positions are varied between different laboratories and different groups. For us, usually we'll have 1 or 2 postdoc positions each year. And usually we post our recruitment advertisement on Inspire Hub and academic jobs online. You can just find, if we have opening positions, usually around October and November. The deadline will be around, usually we set 2 deadlines, one before Christmas, another one probably before February. And you can check. So just check there regularly and you'll see. We have a very nice package. In total, it will be around 280K. This is what you received. This is not before tax. So which is, I would say, a very good salary in China. And also we have 100K research grants. And plus many benefits from the local governments. You can get extra money, actually. I guess Ioannis will tell you more about this. And you'll receive a postdoc apartment if you want to live inside the campus. Of course, you need to pay, not a lot. It's a very nice 1-bedroom apartment with living room, kitchen, and toilet. You can live with your family, no problem. We also have a dedicated postdoc office. Actually, this is one of the postdoc offices. You have a common discussion room, and your office is inside. And also, we have a university-affiliated kindergarten. So if you have kids, if you have children, no problem. We'll help you. And finally, is what I mentioned, Westlake Fellows. So this is a very special independent early career route provided by the universities for exceptional researchers for their early postdoc or just graduated from their PhD, finished their PhD. So this is to let them build an independent program. They have a lot of startup funding and they can hire postdocs. The thing is that they are not professors, so they cannot hire students. It's a 3-year fixed term. It's like postdoc. But you don't need to teach. You have an independent laboratory. You can build your independent team, and this will finally lead to a tenure track after 3-year after the evaluation at the end of this fixed term thing. So if you are interested, these are the deadlines and the informations. You can just check. And you can also apply directly for our tenure track position if you are interested. Yeah. We are a small university, but we still have positions opening. Yes, especially quantum information related. Yeah, that's more or less thing. I show a little bit pictures about our campus facilities. You can find everything you want. And we have a very nice library. We have a very nice swimming pool, fitness room, everything you want. And these are some pictures from the university. The nice view of the university. And there are many activities. Actually, the nice thing is every 2 weeks, we'll have some performance. And you can just go there to watch. And this is a piano performance from a very famous pianist. And there are also many clubs, if you like. I don't know which sports you like, but you can attend one of these clubs to enjoy life here. Yeah, that's more or less the thing. And this is Hangzhou, which is a very nice city. Both have a traditional view and also modernized cities. So if you live, I think Ioannis will tell you more. Since I don't have a lot of time, I just live here. And the stage is Ioannis and Stephanie.
Okay, so Hongguang gave you some general information about what is happening here at Westlake and in China in general, but I would like to talk to you about how I experienced all that. And this experience is actually quite recent since I arrived here in January and I started working officially in February. So first of all, why China? So China is a very beautiful place, and this is actually a photo for sunset at Westlake, and you can see how beautiful this place is. It's amazing, it's efficient, and it's very convenient. We have trains that are very fast, we have very good connections, it's easy travel, which is very important if you're doing research. You need to travel for conferences, and you need this to be quick. You need to avoid going to the airports, waiting for 2 hours there just to go through security and all that. You can just go, take the train, and go wherever you want. So we have daily apps that you'll get familiar with. So WeChat, Alipay are necessary here in order to pay, and they have many, many other mini apps that can be used for other activities. Meituan is the most important thing here. You can order whatever you want, and it can be on your doorstep. You don't need to go out and order anything, buy things. You can just have this app, and they will bring it to you. So how do you get here? So first of all, you need to get an offer. Once you get the offer, then you can start going through the administration process. The most important thing that I had an issue actually, and it delayed me from coming here, is to get your official degree. So having done your defense is not sufficient in order to start your postdoc position. You need to actually have your official degree, and then you can just register in the system, and then you can go through the visa process. Once you have your degree, the whole process will take like a month. It's very fast. You can apply for your visa, and you can get it in like 2 days. After that, you can just fly here and be in China. So this is the whole process for getting here. After you get here, the administration will help you with everything. So the campus is very beautiful. This is actually our library. From outside, library from inside. It's an amazing place. And we have many floors there, and more will be built soon. So it will be good for you to experience that. Canteens, Hongguang also mentioned them. We have different food, Chinese food and Western food here. So you should come and try it. And it's also very, very cheap in comparison with prices in Europe or in the US. It's very, very cheap. You can eat for like €2, a very, very good meal. So coffee shops. We have facilities for swimming, gym, whatever you want. This is the part of the auditorium. Hongguang talked about performances that take place every 2 weeks, roughly. And this is a map of the campus. So we are right here at the moment. You can see that we have running court, football court, many basketball courts. We have a hotel which is right outside the campus, so you can just visit us and be very, very close to everything. On the left side here, you can see the residencies. So here are postdoc and faculty and PhD student residencies. These actual houses is for chair professors, and this is the place we all want to end up at some point. And these are actually the new residencies that are being built at the moment. They're actually built, and they're much newer than these ones here. So this is the auditorium. This is called the academic ring, and this is the library. As you can see, we have a beautiful river that has a walk around it, so you can just walk next to the river. It's quite good, not just for calming you down, but also thinking about research. And yeah, it's an amazing campus. And you should experience that. You should definitely come here and see that. So, on-campus accommodation. It's very important. You can just come here. You can rent a postdoc apartment for $2,400 a month. It's very cheap in comparison with the salary you will get here. And you also don't need to commute every day. You can just be here and just walk to your office, or just work at home if you want to do that. You don't need to worry about any type of bureaucracy. The administration will be there to help you out with every step of the process. They know their job pretty well, and there will be no delays or anything. You don't need to worry about these things. Also, the group integration is very easy. The working language is English, so you just come here and you can also integrate with a group just before coming here. You can attend online group meetings and you can start to understand how your group is actually working. And yeah, this is very important. You have 1 month until you get your visa process, so you can do that and be ready for when you arrive here. So the language, this is one of the main concerns that everyone has before coming here to China. So learning Chinese would be very useful. I tried doing that. I read up to HSK 3 level. It's not sufficient to actually communicate effectively, but you can use some phrases to order or just get in a Didi or stuff like that. But it's not necessary. Inside the campus you can communicate, you can do the research in English, so there is absolutely no problem. But to be honest with you, you will have much better experience if you learn Chinese. And actually, the university can help you with that. We have free courses that can teach you English every semester. And also, you have Chinese culture actually classes that you can attend these if you want and experience the culture and learn how everything works here. Because there should be a culture shock once you arrived here. It's much different than Europe or the US or in the West in general. So you should attend these courses. They're pretty helpful. So as for the research, Hongguang talked a little bit about what we are doing, and here in our group and also in China, we have very diverse research areas. So we're mainly doing quantum gravity, loop quantum gravity, asymptotic safety, effective models, modified gravity, semi-classical gravity, and relativistic quantum information. I'm doing the last 4 parts. I'm not doing the first 2 ones. I'm most interested in black holes, and I think this is more appropriate for me. And one of the concerns that every researcher should have is about his career progression. So first of all, we have support from the government. And except for your salary, you will get benefits. These benefits are tax-free, so everyone wants tax-free money. And this will be given by the government. Every 3 or 6 months, you can apply for something, and you'll get more money. You can get, we have grants, we have that will help you with the research and also with salary increase. So it's very good to be here in terms of money and considering the cost of living. And all of this combined will help you have a good life and also career development as well. And with this, I'll end the career development talk. Thank you. Yeah, so I think we should head to lunch now. Before that, maybe we can gather in the lobby and just take a photo, all of us together. Yeah, that would be good. And we will start again at 1:30. Yeah.
only these terms will give me contribution to the propagator, so I want to study these operators, okay? Also, for some reason, I write here Gauss-Bonnet. It's not obvious, but this maybe, but R tilde is a dualized Riemann tensor, and dualized Riemann tensor squared is nothing but Gauss-Bonnet. And I also want to sandwich it with some form factor. It is not important for propagator, it will be important for the next. Because now, I want to ask a question, actually two questions. First question I want to ask, if it is a most general propagator, I want to ask a question, can it be better than in stellar theory? Can it be without ghosts? Second, once I will establish this, I will want to ask whether it is a well-defined quantum field theory and whether I can compute something. At this level, when I will ask question whether I can compute something, I will compute one loop contribution. It doesn't sound trivial, but I tell in advance that I will compute. Well, not during the talk, but I will demonstrate you what we did. And this guy, particularly this combination, coefficient in front of it will run. So because it will run after one loop computation, I will keep it. Okay? Good. So what else I have to say here? There is some scale. I don't know what the scale, but because we all studied physics, we understand it should be less than Planck mass in order to cure problems of GR. It should not be that small just because we don't observe it. We don't observe it even during inflation, so it should be greater than scale of inflation, most likely. At least this was a result of papers which we wrote about inflation in this model with Alexey Koshelev, and with a try to embed his inflation here. Okay? Now, once again, this is the most general action to study propagator. Okay? This is a statement here. This is why I like it. I don't know how much it is nice, easy or not, but I know that's all I can write. Okay? Now, propagator, I skip computations. Variation of the actions is quite straightforward, even though tedious. This condition simplifies stuff a little bit because this makes graviton propagator simply graviton propagator in GR scaled by something. This something, exponent of minus 2 omega, is just replacement for this long parenthesis. Okay? Chi squared is here, and this long parentheses are here. Okay? Now, here I want to challenge Mr. Ostrogradsky, and I want to say that I can make this stuff to be exponent of entire function. If it is exponent of entire function, then exponent of entire function is yet another entire function, but it is entire function without zero. So it means that I will never have extra poles if omega is entire function. Okay? Then I also notice that exactly same kind of operators I can find in string field theory in the interaction terms. This gives me even more motivation. Now, what I want to do, and because I'm given only half an hour, I will not do it in details, but I will try to explain. I try to make a quantum field theory with such a propagator. Okay? In general, it's not impossible, and you can do it. The problem is, so far, just, how to say, conceptual problem, that omega is just some entire function. You don't know which one. You have infinitely many entire functions. In principle, any polynomial will do the job, in principle. In principle, either not, because a polynomial will be growing too much somewhere on the complex plane. Okay? Now, the problem, my problem now is the following. My problem is that I want to understand something more about this factor. But on the way of understanding this, I understand that in principle it would be great if this guy Fc behaves polynomially for large momenta. Okay? Well, not polynomial, like power law, with some letter q. You can ask me why do I need this, and answer is very simple. Since you change propagator like this, well, first, of course, you want to say that you have great tool simply to make any Feynman graph convergent. Okay? This is obvious because you can put here any suppression you like, essentially. So far it is not constrained. But if you make it too much,
like, for example, exponent of chi squared, okay, then it will be suppressed maybe too much. Essentially, you will not be able to implement power counting. And this will be not easy to judge what is convergent, what is not, because as you know, like in any gauge theory, as long as you have such a factor in the propagator, it will appear also in the vertices. But if in propagators it will suppress, in vertices it will blow up. So you want to make it better, and you want this FC to be power law. So essentially you want omega to behave logarithmically, which is not impossible. It is, if function is entire, it doesn't mean that it cannot behave logarithmically, okay? Now, if you satisfy this requirement, then you can just do power counting in loops, and this is the degree of divergence of some graph with L loops, and you get this number for general graph of L loops, okay? This is just topological computation. From this topological computation, you understand that Q greater than 2, you left only one loop divergent. One loop is always divergent because in one loop, you always have number of vertices equal to the number of propagators. Okay? It's very simple. But the problem is that because it's very simple, in one loop, you always have a divergence. Okay? However, moreover, because you have exactly suppression equal to, let's say, blow up in one loop propagator and vertices, you are kind of will have a local contribution to divergency. So now, what we do super sketchy reminder about what is background field method, where we essentially consider our logarithmic divergence as being expanded in using heat kernel technique, introducing background fields. This is supposed to be some UV cutoff, and mu is our running scale. Okay? Simply because I argued that for Q greater than 2, I need only to worry about one loop, and because I have argued simply on a topological basis, I don't even have to argue. Once you open any book on quantum field theory, you remember that number of propagators is equal number of vertices. So I naturally expect that one loop being divergent is the only divergent contribution here. So now my task is to compute one loop in this gravity action. Okay? Or better to say, compute one loop in for most general propagator. Moreover, maybe it's not obvious, but these guys, box to the power n, give you maximum number of derivatives acting on a metric in one place. Since they give you maximum number of derivatives in one place, they will give you dominant contribution to divergences in graphs. So essentially, even if you will write some operators with similar mass dimension at some level, you can write them, but they will definitely give you subleading contribution. So if I will be able to solve these terms which are written and compute one loop, then I'm, let's say, happy. So what I anticipate, naturally, I anticipate divergence of R squared, Weil squared. I can imagine that there is Gauss-Bonnet, and I can imagine that there is box R-type divergence. These exactly terms which were computed already 50 years ago in one loop contribution to gravity, already in original papers by Wilkowski, who essentially computed one loop effective action for GR. Okay? Because we don't assume any other divergences, we proceed with this, and this will be our beta functions, beta R, beta W, and BE. Okay, this is a boundary term. We drop it. This is a tricky thing, and we are going to keep it anyway, because it will not be exactly topological invariant as long as you think at least about dim-reg, because in dim-reg, Gauss-Bonnet is not topological invariant anymore. Because in dim-reg, you have more than 4 dimensions, and therefore, I mean, not exactly more, but different from 4, okay? So this may be some surprise, and actually what we will find out that this will save us from having some trouble. And now we just compute one loop effective action. For this, we need to compute Hessian This H is a Hessian. This is the most cumbersome stuff. This took us some time to understand, because you understand what the deal is. The deal is to compute Hessian in this action, essentially to compute second variation of this action, yeah, and extract operator in between of H mu nu. This is a highly non-trivial stuff, simply because since it is loops, you have to go off shell, so you cannot anymore use Minkowski or whatever background. Honestly speaking, it's mission impossible. So what we did this for the class of covariantly constant backgrounds. Because if you do it in a general case, you obtain structures which you simply cannot tame as long as you aim to do something with infinite power of derivatives. For covariantly constant backgrounds, well, I didn't write it here. Covariantly constant essentially means that Riemann tensor is annihilated by covariant derivative. Okay, so then Hessian is possible to compute to all orders, as well as possible to compute this delta GH, which is from Ghost contribution. Oh, sorry, it should be H small here. It's from Ghosts, from Fadeev, Popov, Ghost, and this from the gauge fixing term. All of this can be computed. This definitely is the most laborious part. The most laborious part, even just to compute, even if you have a code. Unfortunately, we have it only in Mathematica. It's super laborious to compute. It takes ages, roughly speaking, weeks. But if you are successful in this is the answer which we are kind of happy about. And this kind of the main, nearly the main output of all this activity, that these are final results for beta functions for beta W, beta R, and beta E. These are these coefficients in front of R squared, Weil squared, and Gauss-Bonnet term. Okay? And these are the answers, where we use letter Y, which is just a fraction of these form factors, and letter Q, which determines asymptotic of form factors. So the assumption which is made here is that asymptotics of these form factors are the same. It is not impossible that they are different, but definitely for practical computations, in order to get at least something, we stopped with the fact that we want similar asymptotics, and therefore this ratio is essentially ratio of asymptotics of these form factors. Okay? Now, this is the answer, which you are welcome to check. Intermediate computations are very long, and output of intermediate computations is impossible, even though miraculously referee asked us to provide full intermediate results. And because we wanted paper to be accepted, we submitted 120 pages literally of intermediate steps. But this is a short extract of it, which is already answer for all this B, W, R, E, which now the quest is the following. You have system of algebraic equations, okay? Now you want B, W, and BR to be 0, okay? As simple as that. Now, for our simplification, which we used before, we surprisingly select that there is a single possible value of Q for which this happens, and why. Okay? The simplification which I mean is exactly that we wanted this sum to be 0. We don't have to ask this, but we asked this for simplicity to make propagator of graviton just uniformly scaled. Otherwise, we would have to scale differently scalar and tensor parts, which is possible to do, but not easy to implement in loop computation. So this other way around, well, definitely it can be extended. Since we have done computation in some region, we can extend it. It's just a matter of time, how much you want your workstation to run. To get exactly this, it was running about 3 weeks without stop. Okay? Quite a modern one. Okay, on all its 16 cores, so it's quite a long time, okay, to do all this. Mainly, the main laborious part is computing this Hessian, because it was done analytically, you know, using Mathematica and Exact. Beta E, which I mentioned, is non-zero, so it is running. We don't care about it, because when we reduce to 4 dimensions, it still remains topological invariant. We care about the fact that others can be put to 0. Okay? So, what I want to conclude here? I want to conclude here the following, that we was thinking to consider this class of analytic infinite derivative series. Okay? And we wanted to target the goal of UV complete and unitary gravity, and once again, our claim is the following. We can make these beta functions to be, these coefficients b to be 0. And we claim that this is enough to claim that this model is renormalizable. Okay? Because all the other graphs will be renormalizable by power counting. Okay? And even though, as I say, there are some assumptions here and there about ratio here and asymptotic here, we can, in principle, extend this computation. Now, regarding the model itself, in principle, this model of gravity is quite nice because it accommodates a lot of interesting things, including this and that, and notably Stravinsky inflation and finite Newtonian potential, and also it can have only non-singular black hole solutions in principle. Okay? And then our claim is as simple as that we can choose form factors such that we can have this model renormalizable. We have problems, of course, here. Okay? Problems, the main problem is the last one, but let me start with interesting questions. Interesting questions that we want to understand how this model is compatible with EFT of GR. Okay. Now, we didn't do it yet, or better to say it's not easy at all to compute amplitudes in this model. I think you can appreciate why it is not easy, just because it's difficult to account for infinite tower of derivatives. Okay. Now, the main question which I'm personally interested is to see what the relation between this model and string field theory action, which just by construction has exactly the same kind of form factors acting on fields. Okay? This is not done in any way, and any comment and advice in this direction would be super welcome. Causality, which I mentioned before, is actually a problem. Because normally, you expect that any higher derivative gravity is not causal. Or better to say, paper, I don't remember all the authors, but 2 of them are Maldacen and Zhibayev, and 2 other people I don't remember exactly. They proven explicitly that you can not avoid causality violation as long as you have higher derivative corrections. Let's put it clear. Einstein-Gauss-Bonnet gravity is not causal. Okay? It's not a surprise, actually, because you change light cone. It's okay. in a sense, it's okay. Now, the idea here is that we will cure this problem and we will restore causality. And even though this computation is not yet finalized, the claim is that we should be able to restore causality, and the how to say, crux here is absence of new excitations. Because if you go inside of analysis why causality is broken in higher derivative gravity, usually it happens because you have extra excitations, and these extra poles in the propagator change your light cone, and then they change process where you can test causality, for example, collision of shock waves. Okay? Now, here, if you try to do something, you will understand that most likely this problem will be avoided, okay? And causality will be restored. It's work in progress, okay? But the main issue here, actually this one, that this whole study is presented kind of using heavily the properties of Minkowski or in general maximally symmetric spacetime. When I say using this property, I mean essentially using the fact that we already started with this action with a claim that it is great action around a maximally symmetric spacetime. Of course, if you go to something more complicated, let's say black hole, It will not be end of the story. And I don't know what to say here, really. But I know that in general, yes, I would be happy to see more background-independent construction. I have known it, so this is a good future direction, but for the moment, the claim can be made a bit more modest. Let's say like this. We have constructed massless spin 2 renormalizable theory around Minkowski spacetime. So, and I will stop here. Thank you very much.
Thanks for the nice talk. I understood that by choosing the form factor, the specific form of the form factor, you can regulate the UV divergences. But
Yes.
I'm curious about the IR footprint of this non-locality that you have in your Lagrangian. I mean, specifically, does this UV modification change asymptotic symmetries at null infinity? For example, BMS group or gravitational memory effect?
It should not change IR, or at least you can construct it easily that it does not, simply because you will introduce this scale and make it high enough in order not to change anything. Think about the scale like about Planck mass, or nearly there, and it should not change you anything between 0 and Planck mass. You will see GR in all these energies. We're talking about modification higher than this scale, okay? This scale should be somewhere close to Planck mass. After this, you will have changes. It will not change, it will incur some changes, but not observable for sure. If it was your question.
Yeah, but because it has some non-locality, I would expect some changes in observables.
No, you see, non-locality is non-locality, but non-locality doesn't mean that you... the most severe thing which can be questioned here, I guess, is causality. Causality, you can try to hide under under uncertainty scale if you want. The rest will be changed, but you can make it changed not up to observable scale. Okay. Well, if you want, you can simply lower this scale down. But you know, if you make this MS of order of 1/10, then you should already see it now. So you don't see it. You can make it scale of inflation. You will not see, well, not like you don't see, but you don't need it to explain current inflation, okay? At least until this Atacama telescope, you don't need much of change from Starobinsky model, okay? So until 10 to 16 GeV, you are more or less safe. Okay, plus minus this.
Any other questions?
Thanks for your last talk. And I'm wondering how this UV completion and unitarity and causality constrain your analytic infinity derivative of gravity.
Sorry, say it again.
I mean, how to use, how to apply the UV completion and unitarity, and also the causality to constrain this action.
Well, because different people mean different with unitarity. This construction with an idea that you have this exponent of entire function manifestly kills you any degree of freedom apart from massless graviton. So you will not have anything but massless graviton in the perturbative spectrum, okay? If you want to ask much less trivial question about unitarity of scattering amplitude, this is a good question to understand whether it happens or not, okay? Causality, let's say like this. After this, unfortunately, nothing constrains this omega much, okay? because the only maybe serious constraint is that you want this FC here to go like power law at infinity. This requires some very peculiar form of this omega, but peculiar doesn't mean unique, okay? And essentially for all of this which I was telling here, apart from this asymptotic, nothing else is relevant. So we cannot say much, because IR is like in GR. UV is essentially like this. We just use a magic fact that because it's not brute force this, but rather, so we not just substitute this here. We say that this is just asymptotic, but the whole structure is exponent of entire function. This tells us that we should not have extra poles in the propagator. Whatever in between, so this was IR, this is UV, whatever in between, we have no good idea. Neither we understand can it be constrained or not. And causality itself will only, what I understand from preliminary computation essentially I mean I do standard trick of scattering graviton on a shock wave, okay? Nothing more, nothing less. You send the graviton to the shock wave and scatter. Either you get or not time advance. Your problem is not to get time advance, okay? Because if you get time advance, it's a bit pity, then your graviton appeared before it was emitted, okay? Yeah. This standard computation which people usually do. Then the only fact which will help to prevent it is just the fact of this shape of the form factor here. The rest we cannot constrain, and most likely computation of amplitude will. Okay?
Okay.
If there are no more questions, we should thank the speaker once again.
Okay. This moment. Stop this.
Okay, so our next speaker is Hongguang Liu, and he will talk to us about clocks, observers, and relational locality in quantum gravity. Hongguang, the floor is yours.
Okay. Okay, so I'm here again. So thanks for the introduction and organizing the conference. Yeah, thanks for the effort. So I'll talk about something which is more related to RQI, of course. This is mostly based on the canonical gravity discretized approach. So as I said, it's Gaussian dust, more or less, in finite cutoff quantum gravity. So if you are not familiar with notions, I'll introduce through this talk. The starting point is we all know that canonical gravity, or I mean, even I can remove the canonical gravity, is a constraint system. Constraint systems in the sense that, so these PQ are canonical variables. So on the lattice, you can use I in the continuum limit, I just label the orthometric and conjugate moment degree freedom. And then if you look at the thing, there is what we call Hamiltonian constraint, which is a scalar constraint, and also spatial diffeomorphism constraint. And in total, you have these 4 space-time diffeomorphism constraints. They are constraints such that they generate gauge transformations instead of the standard time evolution. So this already telling you that in gravity there is no time. Actually, the time, what usually when you solve Einstein equation, you have a time, but that's only a coordinate time. Coordinate time is not physics because gauge transformations changes it. So these are just labels. These are not observables. We all know that in any quantum theory, an observable with gauge transformations, an observable means that it's gauge invariant. But unfortunately, in gravity things, gauge transformation, general time evolution, or space translation, these are not observables. So to define observables, we need extra things. So there are different ways to define clocks and rules, which are a spatial coordinate if you want. If one have boundary, for example, if one have a simply flat space-time, of course there you have automatically a coordinate, and then you can use geodesics, extend them into the back. But if you think, if you are in a different situation, for example, if you are a compact manifold, or if you in such case that you don't have boundaries, then you really need extra things for your system to have a clock and rules. So usually we use matter field. These are the extra things. It's not gravity itself, because gravity itself cannot define this clock and rules. So this is more or less why a quantum gravity, which we want to really define physical observables, it must be relational. Otherwise, the only thing we can see is the global feature, which are somehow, in some sense, topological, or only relate to the differential structure if you want. So the relational question here is, so suppose we have a field F, and we need to ask what is the value of F when physical clock and rules has some certain readings. We cannot ask what is F on some coordinates, because we don't have coordinate is not physical. That's the basic thing. Sorry. Yeah. Okay. So this is our idea. Basically, we need to introduce, since we have 4 diffeomorphism constraints in 4-dimensional space-time, we need to introduce 4 matter field. So we have a matter field defined for time and 3 matter field defined for the rules, for the space, for the spatial direction. And gravity and matter, they are described relatively to some reading. Reading means we give this 4 field a value. We read them at certain values. And then we can define our gravity field relative to these readings. So basically, the idea, the whole story is that using this, we first have partial observables. Then we need to really solve this diffeomorphism constraint or gauge constraint. I mean, if we have also SU2, like in loop quantum gravity, we also need to solve the Gauss constraint. These are extra things. And then we have a condition on reading. It depends on we have a very ideal reading, like we have delta distribution, or a standard POVM reading, which you don't have a delta, you have some Gaussian-like reading. And then we have the final relation of physics defined on the whole system. These are more or less the story we want to achieve. So, I mean, up to now, we have different notions how to define this reading. The first thing is you can understand as prospective neutral. In the things we solve, we keep all the matter field quantum, and we solve the whole constraint contains both gravity and matter at quantum level. And then we all have a physical state. The physical state is not only gravity, it's gravity plus matter, but they represent the entire gauge orbit. This is perspective neutral. And then we use quantum reference free to pick observer to read the things. And there is another thing, which is reduced phase space. This is usually the way that already developed a lot in loop quantum gravity community, is the thing that one first fix the reading. Basically, one already do gauge fix before one solve the constraint quantum mechanically. And then, so after fix the reading, you basically solve the constraint classically. After that, you have physical Hamiltonian. And then one can quantize the physical Hamiltonian, because once one have a physical Hamiltonian, the system becomes the similar thing as quantum field theory, because now you have time, you have space coordinates. You don't have the problem of clocks. So I'll discuss the relation between these things. I mean, reduction and unfolding basically I'll relate how the reduced phase space can go back to the Dirac perspective or perspective neutral way. And also how to start from Dirac states, which we basically solve constraint quantum mechanically, to a conditional perspective in quantum reference frame. Okay. So the setup is a naive toy model, which is what I call finite cutoff discrete QG. Because if it's continuum QG, we have a lot of problems. We don't know how to solve the constraint. So basically, what is finite cutoff discrete QG is basically we discretize the thing into a lattice. But this lattice, what we call final graph, is abstract lattice. It's not a real lattice, not like lattice QCD that you have really lattice on your space-time point. These lattices are really abstract lattice. Gravity will tell you what is the distance of this lattice. And once we have finite graph, actually this can be understood as a circular decomposition with manifold, but abstract. So we have vertices and edges as the labeling of this graph. And the Hilbert space, the kinematic Hilbert space, before we solve these constraints, is what I call data Hilbert space, which is basically the graviton part, tensor product, or the matter part. I'll tell you that I use Gaussian dust, so the matter part is just R to the fourth, basically because we have 4 matter field on each vertex. So this is very simple. And you can already see what happens if you go to the continuum limit, this part diverges. That's why we need a finite cutoff at this toy model. I'll discuss what is the continuum limit afterwards as outlook. Yeah. But basically, these are our setups. So if you are familiar with RQG, basically for the data Hilbert space, you can use the standard holonomy flux example, which you have SU2 on each axis and caution out the gauge transformations on each vertices. I mean, this is also the same Hilbert space for SU2 young mirrors. The difference is that here the graph is really abstract graph. That's what I want to emphasize, that these vertices and edges or links, they are just labels. They don't have any physical location. That's important. All the physical location readings are from a relational framework, and also the geometric reading from the gravity. Okay, so this is setup. I also want to explain why I want to use Gaussian dust. Gaussian dust is very special matter field. If you want, this is Lagrangian. So if you look at the Lagrangian, it actually contains 4 Lagrangian multipliers. One Lagrangian multiplier is the density, and there are 3 Lagrangian multipliers related to the spatial part, to the speed. So these 2 equations, if you do variational principle, I mean, this basically gives you 4 constraints. The first constraint is this one. The second, the spatial one is this one. If you look at the energy momentum tensor, you'll find that this is exactly a matter field that only has the density that doesn't have any pressure. Here, t is the time, which you can choose basically t as time, and this gives you a free-falling observer. Si, these are comoving labels. So t and si basically give you a coordinate reading along this free-falling observer. Rho and wi, they are accelerate, they are Lagrangian multiplier. If you want, you can eliminate them before quantization from second-class constraints, from solving a second-class constraint. The good thing is, since this whole system is dust, is pressureless, there is no propagating degree freedom. No propagating degree freedom means that you can have a clear separation between your gravity mode and your observer reading. It doesn't destroy the thing. If you use a scalar field, standard scalar field, it has a propagating degree freedom. And once you want to use it to be an observer, then your physical Hamiltonian will essentially become no local because you need to collect all the information that the propagating mode has. But using dust, you don't have this problem. So you can have a very local physical Hamiltonian afterwards. This is the advantage. Another good point about dust is really a reference frame that you have a limit where you can neglect, where the back reaction is negligible. The reason is very simple because if you look at the density and also this Wi, these are just related to the gravitational part. So you can basically, since there is no inverse power of density appears in your definition of the momentum and so on, you can really set the density goes to 0. It doesn't destroy your constraint system. So in the sense that in this limit, you can keep the clock and root Hilbert space, and you can really suppress all the dust back reaction to your gravity. And in this limit, somehow you go to the Perche R sector, but you still have your clock and root Hilbert space. So this becomes the perfect test observer if you want. Okay, I mean, of course, physically you need to really make sure that your physical Hamiltonian has 0 in its spectrum. But this depends on your quantization procedure. But more or less, classically, this is allowed. Yes, and now we go to really the physics. So what happens is that after you eliminating this auxiliary density field, you got 4 constraints. Basically, these 4 constraints relate. This constraint tells you that what is the momenta, and also this is the momenta of the t, this is the momenta with respect to Si. These are somehow called linearized constraints because if you look inside this H, it doesn't depend on the momenta. And once you have this property, you have a nice thing because now you can form a really strongly abelian constraint. I mean, these are equivalent gravity constraints with matter, but now they can be abelianized. This is very important because we all know that if there is no P, the original graviton constraint forms what's so-called Dirac hypersurface deformation algebra. It's not a Lie algebra, it's a Lie algebroid, because the structure constant depends on the metric, depends on the inverse metric, actually. But with matter field, actually, especially in this very simple setting, you can really form a strongly abelian constraint. It's not weakly commuted, they are strongly commute. And this strongly abelian constraint actually can be written as a Hamiltonian connection. So this is the flatness condition on the Hamiltonian connection. So this partial A and partial B need to be think as derivative with respect to the field. And HA, HB is this H, they forms a flat connection. This is basically what happens in this matter field deparametrized Hamiltonian. Okay, and now, I mean, this is in the continuum. But if you think what happens, once you cut off everything on lattice, you have a problem. Because the previously strong commuting constraint, because they are flat connections, once you discretize them, they become no commuting anymore, not commuting anymore, because you always have the lattice effect. Because lattice effect basically destroys your original symmetry. Then you all have I mean, this is quantum, of course. You all have your curvature on the Hamiltonian flow is no 0 anymore. So this causes a big problem because if you want, when we quantize, of course, we need the algebra and all the clock readings, all the later on beautiful thing will rely on. We have abelianized constraint, which forms the algebra and strongly commuting, which is a very simple system. Once we lose this property, we are in trouble. So we need to solve this problem. But if you look, this finite cutoff problem actually written in this operator curvature is very simple. It's just an anomaly problem on the curvature. So we propose some method to kill this problem. Is basically, if you think this is basically how to remove the anomaly for a flat connection of flat curvature. There are standard ways to do this. Is basically introduce, if you want, a path along the connection. And what is the connection? The connection is basically the connection I showed you before. Is this HA or HB is a Hamiltonian connection. And once you have a Hamiltonian connection, of course, you can introduce the right invariant vector field with respect to this connection. Basically, this gives you the Poisson bracket between the connection and your field. And then you just write out holonomies with respect to this connection. And once you write holonomies, you can define really, again, a new flat connection from the standard method to the derivatives. From the group, if you want. And after you do this method, you find that this flat connection defined from the raw connection, which in principle doesn't commute, becomes commuting. And this is basically a Amaro-Cartan method how to derive a flat connection from a raw connection. And this basically tells you that after you do this, you do have finally a linearized algebra of the constraint, even on the lattice. So of course, this is classical, but quantum is exactly the same thing. You just need to bring all the Poisson bracket to commutators. So of course, once you bring all the Poisson bracket to commutators, you introduce H-bar corrections. But you can show that this actually is preserved in the classical limit. Basically, when H-bar goes to 0, your raw, and in the continuum limit, of course, this is what you need to make sure that once you go back to continuum limit, your flat connection need to be exactly the classical connection. Otherwise, you have a problem. You do some trick, and you destroy your original system, even they are commuting. So this is what you need to keep. And fortunately, with this construction, you can show that the flat connection and the original raw connection, they are exactly the same thing up to the lattice effect. So in the sense that once you remove the lattice artifact, you go back to your continuum limit. So this is good. And then, as I said, then you quantize this thing. Is basically you bring everything to operators. And your original momenta becomes a derivative with respect to your matter field. And then you can bring everything into operators. This U is basically the holonomy, if you want, of the Hamiltonian. But in other words, if you look at this, in a coordinate reading, this actually becomes dt. So this is exactly your physical Hamiltonian integrated over the thing. I mean, in other words, this is like the evolution operator. So this is how your evolution operator automatically appears in this system. And if you look at finally what is our constraint, it's basically the Heisenberg picture of your clock reading, right? So this is basically what happens. Yeah, and then you can solve this physical Hilbert space. And now you have a commuting constraint, and your constraint basically is somehow in this form, where HI is afterwards you commuting the forms of flat connection, if you want. And this HI, this solution turns out to be exactly this UZ, which is exactly this U, acting on your original data wave function. Data wave function is our gravitational part. So this is how everything appears. Now looks like a evolution system with data reading. But now it's not exactly data reading because this is field. This is not a coordinate. And since I don't have a lot of time, I just tell you that what is a clock reading is basically now you insert. This is like a delta reading because you exactly insert a reading of your field, your matter field, into the evolution operator. Now you get exact standard physical evolution on your physical Hilbert space. And this finally relate your data Hilbert space into a Schrödinger picture for the physical states. Yes. I can skip this. Basically, I want to remind you what happens here, but basically eta is a group averaging because when you solve the constraint, actually what you use is a group averaging process. You go to the physical Hilbert space, And Q is basically a fixing of data, if you want, fix the global data representation into your data harbor space. And this is a clock reading, basically, is a sharp clock reading. It's not POVM, because basically it's evaluate your matter field at exact some reading. Yeah, and then of course you can introduce POVM, which basically you now use a POVM with some width like that. And this unitary transformation now is exactly moving your original region of the reading, yeah, which is exact the thing. And of course you can really define a POVM measurement using some like Gaussian function peaked at a classical value with some uncertainty. This is how you get finally POVM or physical reading. Yeah. Okay. I can skip this. I guess it's too technical. I also want to talk about what happens in a reduced phase space framework. Basically, what happens in reduced phase space framework is that you directly solve this at classical level, and then what you quantize is exactly a physical Hamiltonian. But before you do that, remember you have ungauge fixed action. Everything there is ungauge fixed. What you need to do is to ungauge fix everything if you want. What you solved is you give that a reading at the physical time. This is the gauge fixing condition, and then you solve the constraint, which basically you solve all the momenta. And in the meantime, you also give your lapse function a reading, because in the dust frame, I didn't write it here, but in the dust frame, it also automatically fix your lapse to be 1, because you give t a physical value. It also fix your lapse and shift. So the thing is, if you think you can do unfolding, but you need to read out what is your lapse. There are 2 gauge fixings, yes. One is the gauge fixing of already solved constraint, another is the gauge fixing of the lapse. When you do gauge fixing, this is already the thing. But somehow, once you have a quantum theory, somehow it's hard to read out of the lapse. Gaussian doesn't have this problem, because for Gaussian, the lapse is always 1. If you use the scalar field, there is a problem, because you only have the physical Hamiltonian. You need to know what is really your lapse. But then once you do reduced phase space, you kind of lose this information, because you only have physical Hamiltonian. That's one of the problems. I show a very simple example if you are familiar with bouncing models. In this quantum theory, your Hamiltonian becomes this. Then it's really hard to distinguish what is lapse, because in classical theory, what is lapse? If you have a scalar field, basically your physical Hamiltonian becomes a function with your original GR. Oh, sorry. And then your lapse is just the f prime, because this gives you time evolution. But once your Hamiltonian, classical Hamiltonian, get polymerized, it's hard to distinguish what is lapse, because here you can read lapse as cosine, but actually it's not. You have another lapse. Okay, so this is more or less the tricky thing. But otherwise, since I don't have a lot of time, except that you can really do ungauge fixing. This already, back to 10 years ago, there already some discussion in Thomas and Mushin's paper. But really, if you really ungauge fix, what I want to emphasize is that you need to know the lapse. And once you know the lapse, you have really the ungauge fixing thing. And then you have an equivalent description between the reduced phase space and also the Dirac quantization. Yes. And in this framework, of course, we have perspective neutral with our Dirac constraint. So we have a very simple transformation between different clocks, because it's just you do the inverse of the gauge fixing clock reading, exact clock reading. You go to the data harbor space, and then you do another clock reading. This is very simple. And you can also ask what happens when you have a reading slice, because you can really define a region algebra. We have a lattice. Just pick some set of lattice field. You define a subregion of your lattice. This is spatial. But since now we have really a time evolution defined with the matter field, you can really define a region algebra from the original reading, basically then you can really have the double commuted. This is how double commutant or causal origins make sense, because it's basically generated by your physical Hamiltonian with respect to reading. I mean, you don't need to know, and actually you don't know what is the original causal origin. You have a spatial slice, basically just some lattice points. And once you have this clock reading, then you can really define a causal origin generated arithmetically by a model Hamiltonian, if you want, in this technical language. But one more thing is, this one, of course, is defined with exact reading. This is ideal. There is no fluctuations. Once you have POVM, you have fluctuations. Once you have fluctuations, your causal origin is also fluctuating. This is the price to pay. I mean, algebras are defined there, but your whole causal origin is actually with respect to your fluctuating of the POVM. Yes. Since I don't have a lot of time, I want to directly go to the final thing I want to mention. Because this is lattice, of course, we finally want to go to the continuum. Well, in quantum field theory, we know something we can already define on the lattice, for example, the relative entropy, if we have several regions. This, in principle, has a continuum limit. Algebra usually doesn't have a continuum limit. I mean, all they converge to top 3. Here we are gravity. It's even harder. We don't know what is the continuum limit. So ideally, we would have a top 2, but we don't know. But at least one can compare the relative entropy. Here I want to discuss another thing is really how to go to the continuum limit. Of course, we need to do some relational renormalization. And we can really go to RR physics, for example. But to do renormalization, there are actually two notions of relational observables, or relational meanings. So one is the relational observable, because now we need, first of all, we need to have an observer. We need to have time and space. These are defined by relational observer. Another thing is we need to have a physical scale. If you think in Wilson RG, when we do renormalization, we have a scale defined as the momenta cutoff. This is a physical scale. In quantum gravity, unfortunately, everything is quantum. The scale is also quantum. It's not it's something we defined before. So one must define another thing, which is what we call relational RG. This is the ongoing work with Muxin and Renata Ferro. Then one need to also define some physical scales actually defined from the geometry. This is also a relational notion that all the scales are relational. It needs to be defined from some readings of the gravitational operators. This is something I want to emphasize, and actually there are two notions of relation. Yes. Finally, I want to make some comments. This is only very simple comments. That, of course, in this setting, where on lattice, we can really, after we do this matter field and causal origins, we can really define a von Neumann algebra. But this von Neumann algebra we have, since we are on the lattice, of course, it's type 1. It's type 1, but it's not a vector because basically we have no trivial connections on links. So we need to have the edge boundary Hilbert space, boundary modes, edge modes. This gives you a type 1, no factor. But this doesn't directly give you type 2 because in principle you need to go to continuum limit, even we solve the diffeomorphism constraint. Yeah, this is something I want to make clear, even we have clock transformations. Yeah, so in these things we are still not the standard model of law which given, for example, by Witten's paper where you can turn a type 3 into type 2 infinity, or you have a corner algebra, but we are currently different from them. Then one need to ask the question, what happens in your continuum limit? And that's really the next step. Yeah. Somehow I can stop here. So I just leave 2 sentences. So we have a flattening of the Hamiltonian, which basically removes the anomaly, makes everything well defined. And then we have relational observables. I think I run out of power, but it's perfect time. Okay, thank you.
Any questions?
Thank you. I have a question. coordinate transformation classically is trivial, but when your clock is a quantum object in a superposition, if you want to jump to your clock, then it can entangle you to the rest of the universe. So I am curious if your discrete framework preserved the locality or it introduced non-local correlations.
I mean, clock transformation in this framework is quite easy because you just do inverse. You go to your data hyperspace first.
Yes, I understood this, but does it introduce non-local correlations? Or?
I mean, you always have I would call it quasi-local because all the clock readings are really not local. You need a tube region around your reading. This is always the thing happens. Yeah, that's why, I mean, it's not exactly local, but it's also not very no-local, right? I mean, and this is also related to what is really a causal region in quantum gravity. I mean, with this thing, you cannot define really a strict, no-fluctuating causal region, but it's always some tube around something.
Another short question. You mentioned that your DOS, at the end of your talk, you said something about relational renormalization group.
Yeah.
And my question is that if the Gaussian dust undergoes the renormalization or it serves as a fixed background?
Currently, it's still a fixed background because for Gaussian dust, there's really nothing to flow. I mean, its clock reading defines your coordinate. It gives you, I mean, it's like reduced phase space quantization. It gives you physical Hamiltonian. Usually, I just use exact reading. It's more or less reduced phase space. The thing is, the relational scale is defined, for example, with respect to your geometric operators. One thing is, for example, once you do hit kernel expansion or I mean, in FRG, for example, you need a cutoff. The cutoff is, of course, on your Laplacian operator. But if you think the Laplacian operator now depends on your background.
Okay.
So your cutoff need to define the respect to a background, background geometry. That's how relational framework plays a role. Because you are cutting the spectrum of a Laplacian operator, which depends on some quantum gravity background. Yeah.
Thank you.
Thanks. I think I'm not familiar with this field. Could you explain more like what's the meaning of the dust in this system? It's kind of like extra degree for freedom associated with the clock.
Freedom. Yeah.
You mean like something different from the gravity or like the fundamental field in the space-time?
Well, usually you don't regard them as a fundamental field. That's why I mentioned dust has a nice properties and really you can turn it off. It's like a toy model, but you can turn the dust off, then go to the purely gravity sector with some test observer. So dust here is really like test observer because it doesn't propagate, so it doesn't give you new propagating modes.
And in this decomposition, like for the reference or the clock, except for the time direction, like the time, you also have like the spatial rod reactions. Yeah. But that spatial part is really necessary. For example, the simple example we have this, like the clock is in the ADS safety case, the safety boundary provided the clock, but you don't have to put the clock everywhere in the book. So yeah. It sounds like you only need a time reaction will be enough.
Yeah, that's a very good point. I mean, actually, it depends on the setting. For example, if you have only ADS, you already have a solution. In that case, you don't need the spatial part. But once you are in full gravity, you don't talk about ADS, you have everything fluctuating, then you, of course, need it. One simple example, I think, is, for example, in GT gravity, you really don't need them because it's topological in the back. Then you can simply solve the back action, you get the boundary Schwarzen.
So basically here, you want to put the clock everywhere in the book.
Yes, but you have the freedom to turn it off.
Right.
Since they are also test observers, especially in this GT setting, you can really turn it off. You integrate out what is in the back, you get the boundary Schwarzen action.
Okay, got it.
Yeah.
Thanks.
Any more questions? Okay, let's thank the speaker once again. guess you will introduce me now. I guess you will introduce me now.
Okay. Yeah, okay, so our next speaker is Ioannis. He's a postdoc at Westlake University, and he'll present us from no vacuum to vacuum regular black holes, the thermodynamics and singularity resolution. Yeah.
Thank you, Hongguang, for the introduction and helping me organize this RQI circuit. And thanks, everyone, for being here today. So I'd like to talk to you about thermodynamics in general and basically about regular black holes. But first of all, I would like to start with what is ultra-compact objects and why we want to study them. So ultra-compact objects are objects that are compact enough to have a light ring, and we know that they exist in nature as the Event Horizon Telescope has taken photographs of them, although their true nature remains obscure. Typically, we model objects like that using the Kerr metric, but we know that the Kerr metric is problematic in many ways. We have singularities that typically signal the breakdown of the theory of general relativity, and we also have event horizons which are in principle unobservable. So efforts in the literature have been concentrated into finding alternative configurations for this type of objects, and one of them that I will talk about today is regular black holes, which are basically objects that are trapped regions of space-time that are bounded by horizons, and they are devoid of singularities. And other type of configurations are horizonless ones, so typically regular compact objects that have no singularities or horizons. So basically the solutions I'm going to talk about today is these two, and this is for two reasons. If we expect that we have a quantum gravity theory, this theory should be able to resolve this type of singularities, so we expect some kind of regular objects. And the second reason is because our metrics, the metrics I'm going to talk about today, just by varying their parameters, we can actually have both of these type of configurations. So I should talk first about how we obtain these solutions and how we achieve this regularization. And we know that GR is described by this action. So if we want to achieve regular solutions, we need to modify this somehow. And to do that, we can do it either by modifying the gravitational sector, so having some higher order curvature corrections. And today I'm going to talk basically about two of these types, so quasi-topological gravity and some kind of polymerized Hamiltonians that have some fully covariant equivalent action. So in this case, the solutions that I'm going to describe are vacuum solutions, so we do not need any additional matter fields to generate them, so they will be purely vacuum ones. And the second way to do that is by adding some matter fields. So basically modifying this matter sector, and sometimes these matter fields will be exotic. So the matter sector that I'm going to talk about today is nonlinear electrodynamics, which is a well-known method to actually obtain such regular solutions. So in this case, we will have the GR theory, and we will have on the right-hand side energy momentum tensor, which is non-zero. And I will talk about how, in what way we can actually generate them. So this will be the example of non-vacuum regular black holes. So I'll take these two, I'll describe how we generate metrics through them, and then I'll describe the thermodynamic properties and compare them. So first of all, I'd like to start with pure gravity, and I will start with quasi-topological gravity. So recently there was a paper by Bueno, Kahn, and Hennigar, and in this case, they showed that if we have a polynomial quasi-topological gravity, we can actually generate these vacuum regular black hole solutions for dimensions 5 or greater, and it's achieved by an infinite tower of curvature corrections, as I will show you. But also, after that, there were non-polynomial gravities that can actually generate a D equal 4 regular solutions by Joanna and Carvalho Rubio. So, the quasi-topological gravity that I'm going to talk about today is basically the polynomial one. And the action that I will have is basically given by this formula, where the Lagrangian will depend on the metric tensor and some polynomials of this curvature. So in general, we expect to have this type of Lagrangian with a series of curvature terms here. I will not show the explicit relation, but there is a specific way that we can actually have a recursive relation that will obtain this type of curvature corrections. So the equations of motion that we get generically is basically this. And you can see that the first two terms are basically second order for the equations of motion, but we have this term that actually generate higher order derivatives of the metric tensor. And this is generically not good, so we need to eliminate this term. So if we do that generically, we go back to Lovelock theory, but here we want to have something more generic. So what we do is we take this term to vanish, but we do it only on spherically symmetric backgrounds. So doing that, we will obtain second order equations of motion for this quasi-topological gravity theory. And this is the way that we can actually obtain the recursive relation for this term. So as I said, this is the action, and I showed that we have up to a number n, the summation here. And what was shown by in this paper here is that if we take this to be infinite, then we can have for a spherically symmetric metric an expansion close to the center that is given in this form. And when n goes to infinity, we obtain a de Sitter core which is sufficient to provide regularity for our space-time close to the center. So in this case, we will have equations that are written in this very, very simple form. And the right-hand side is in the case that we will want to add some matter fields in our theory, but I will not talk about today. We have done some example where we added some electric fields and nonlinear electrodynamic fields in this paper, but I will mainly focus on vacuum case. So this h psi here is basically a resummation function, and we have this summation where psi is basically this term here. And an are basically parameters that are connected to the coupling constants of the theory here. And these coupling constants will ultimately provide us with a minimal length scale required to have the regularity that we want for our metric. So a well-known example is basically picking this resummation function in this form and having the coupling constants in this way. Then we can have this solution here, which is basically the Hayward model, the d-dimensional Hayward model. And this is valid for d greater or equal than 5 in our case. The parameter alpha here that I was talking about is basically coming from the coupling constant and is the minimal length scale that we require for the regularization. So when alpha goes to 0, our theory reduces to Einstein-Hilbert and we get the Schwarzschild solution. So if we want to add matter fields or cosmological constant, then this Hsi will be equated to this form here, and will be the integration constant from integrating this equation. And if we want to add matter fields, it will be written in this form here. So this was one way to generate regular solution. The second solution is basically the work we're doing here with Hongguang. So he talked about the dust and how we use it for deparameterization. So we have a metric written in this form. We have the Hamiltonian constraint, we have the gravitational part, and we have the dust part. So in this case, if we do the calculation, we can show that this gravitational constraint is written in this form, where Hs is basically a shell Hamiltonian, which is described in this form. So here the variables b and v are basically canonical variables attached to this shell. Doing the shell description is very useful because using the LTB framework, we can actually have this decoupling between the separate shells, and we can actually describe their evolution much easier. So the key point here is that we set the density of the dust to go to 0. Once we do that, we can have this shell Hamiltonian. We can integrate this gravitational constraint because this term will vanish, and we'll have the shell Hamiltonian being basically a constant. So in this case, we'll have what we call the polymerized vacuum solution, and this is basically inspired by loop quantum gravity. So doing this analysis, doing the canonical analysis, having the equations of motion and all that, we can actually show that this H0 term appearing in the shell Hamiltonian will give this type of solution. This is because H0 is basically dependent on B and R1. So the right-hand side should also depend on B and R1. And if we want that, 1 minus f over r squared should also depend on B and R1, but this should happen through H0 if we want to have uniqueness and not have conflicts in our description. So doing that and basically having this vacuum solution, we can show that we have a generic solution for the spherically symmetric case, which is written in this form. And all the corrections come through the ratio 2m over r cubed for the d equal 4 case. And this f tilde function basically has all the corrections that we want in our theory, and in principle we will use it to generate the quantum gravity corrections. So this was for the flat case. We can easily actually incorporate a cosmological constant in that, and this is what I'm going to talk about now because I'll use it for the ADS spacetime in order to talk about thermodynamics. So again, we do the same process. The only difference now is that we will have a new term, the constraint for the cosmological constant, which is basically a volume one, and we will have a new HS shell Hamiltonian. We do again the same analysis, and we take the polymerized vacuum case where we'll send the density of the dust to 0. And then we'll have again solutions where now our corrections will also include the ADS length. So when this length goes to infinity, we go back to the flat case and we have the typical dependence that I showed in the previous slide. So this was done in a recent work with Sepide, and based on that, we will describe thermodynamic solutions. So up to this point, I talked only about vacuum case, and now we'll talk about what we do in GR by having nonlinear electrodynamics. So the action will be written in this form. We have the Einstein-Hilbert action. We have the matter field Lagrangian, which is basically dependent in the cases I will describe only on the field strength F. So F is basically the contraction of F mu nu with itself. And the crucial part to understand here is that in order to have these regular solutions, we need a magnetic charge. We need to include a magnetic charge, which is basically the only way to actually have this minimal length scale required for regularity. And specifically, we have no electric charge. The four potential will be written in this form. We have the usual definition for F mu nu, and this will be required, and I'll show you some examples of metrics how this can be used. So one well-known regular model is basically the Hayward model. In this case, we have a metric function written in this form. We will need nonlinear electrodynamics Lagrangian written in this form, where alpha is basically a coupling constant here, and F will depend on the magnetic charge, as I showed in the previous slide. So the weak field limit of this Lagrangian is basically f to the power 3 over 2, which is rather unphysical, because if we expect to have a weak field limit, this should be the Maxwell limit even in this case. The parameters of the theory can be picked in this way, and L is basically the regularization parameter, and as you can see, is directly related to the magnetic charge. So when the magnetic charge is 0, we retrieve the Einstein-Hilbert action, and basically we have no regularity anymore. We have the typical Schwarzschild solution. There are other regular black hole models in the literature. I'll show two more. Bardeen is one of them. Again, we can have a Lagrangian. We can have a weak field limit. Again, it's not the Maxwell one, and different parameters for the coupling constant and the magnetic charge. So the most interesting case is basically a model proposed by Cadone and his collaborators recently, where we have a Lagrangian here that actually admits the weak field limit, and that avoids many of the causality issues that are present. And we have a paper with Sebastian Merck on light rings, and we describe in detail what is happening in the case of causality and the weak field limit and how they are related. So this is the model I will actually use when I talk about thermodynamics. So before I proceed, I would like to show you how this regularization is achieved. So as I said, we need to have a core which will be a de Sitter or an anti-de Sitter one in order to have this regularity at the center. So we expect to have a behavior close to the center for the metric function written in this form. Based on this alpha there, If alpha is 0, we'll have a Minkowski core. If it's negative, we'll have a de Sitter core. And if it's positive, we'll have an anti-de Sitter core. And you can see these examples here. For example, the dashed lines represent the Sitter core. You can see the behavior here. The dashed lines go down. And for the anti-de Sitter case, they will be going up. The other interesting thing here is that if we keep the mass fixed and we start varying this length, you can see that you can get different configurations. For example, if you look at the dashed blue line, you will have 2 zeros for f of r function. That means we have 2 horizons, inner and outer one. If you start increasing this L, you will have these roots merging at some point, and when this happens, you have just an extremal horizon. And then if you increase it even further, you will have basically a horizonless configuration. And this is why I said in the beginning that we can describe just by a metric function all of these type of configurations. So in the polymerized case, as I said, we can have the corrections implemented through this f tilde function. And by picking this f tilde written in this way, we can actually source the Hayward model. And recently in the literature, people have been talking about how to obtain anti-de Sitter cores. In order to do that, we actually need to modify this f tilde function and implement assigned chains close to the center. If we do that, we can achieve regularization through anti-de Sitter core. And this is basically what I will talk about later in thermodynamics and how this affects some of the thermodynamic properties when we compare different types of cores. So, example of solutions in this case, there are many. So we can have the odd models pretty much are de Sitter core, and their counterparts include this modification term here that we can achieve the ADS case. But I'll mainly talk only about the first 2 models, which is the Hayward, and it's a very well-known model. So now the asymptotic behavior has been changed because we are talking about ADS solutions. So now I'll proceed with thermodynamics. So we know since papers from Hawking, when we apply quantum field theory in curved spacetime, we can assign some thermodynamic properties to black holes. We can have temperature, we can have entropy, and this is done by having Hawking radiation, which provides this thermal equilibrium that we need to proceed with a thermodynamic description. And as we're talking about thermodynamic systems, as ordinary systems have some phase structure, the same we expect for black holes as well. And the thermodynamically preferred phase will always be the one that minimizes the free energy. So what was done by Hawking and Page is basically doing this analysis for the case of a Schwarzschild black hole in ADS spacetime. Doing that, we will have a parametric plot of the free energy with respect to the temperature. And there are different phases in this model. So the blue line will present a small black hole. So as we increase the horizon radius, we go like that. But this region here, f equals 0, is basically the radiation part. So as we increase the temperature, we eventually reach this point, which is the Hawking-Page transition temperature. So in this case, the thermodynamically stable phase will be the large black hole. And in the reverse way, when we decrease the temperature, we will have the thermodynamical phase to be the stable one to be the radiation. Now, it's interesting to see how regularization affects this kind of phase structure. And first of all, we've done that with Phil Simovich, that he is now at the Perimeter Institute at the University of Waterloo as an associate professor. And we studied what's happening with nonlinear electrodynamics. And we showed that the phase structure is basically described in this way, where we'll have a small to large black hole phase transition here instead of the Hawking-Page transition. And this is because the line f equals 0 is not anymore accessible in this case. And this is because we have charge. We said that the regularity is supported only when the magnetic charge is non-zero. And in this case, since we have non-zero charge, we cannot allow for complete evaporation of the black hole. We cannot have charge radiation. So this was the case for nonlinear electrodynamics in d equals 4. Then we proceeded with a study of quasi-topological gravity. We did that for t equals 5, where the Hawking-Page transition now is allowed. The phase structure is similar. And it's allowed because we're talking about vacuum solutions, so now complete evaporation is possible. As we increase the space-time dimensions, for example, at d equals 7, while the phase structure remains similar, then the dominant transition changes. So at this point, the little triangle here will have a triple point. And at this triple point, we are talking about a coexistence between a small black hole, a large black hole, and radiation at the same time. While as we increase the temperature, then the dominant transition will just be the small to large one. Same at d equal 9, then we will have the dominant transition to be the small to large, and we will not have the transition to radiation anymore as the dominant one. So then we studied what's happening with the polymerized vacuum case. You see again that the phase structure is similar, but now we compared in this case what is happening if we pick a different regularization core. So for DS core, we will have basically the solid lines, and as you can see, Hawking phase transition occurs because again they are vacuum solutions, and we have the added de Sitter core written in given by these dashed lines here. So dominant transition will be the Hawking phase in both cases, so the type of regularization core will not basically affect the phase structure. But what it affects is basically the Hawking phase temperature. So initially for small ADS length over minimal length scale, you will see that the DS core has lower temperature in comparison with ADS core, basically for the Hawking phase transition, while this behavior changes as we increase this ratio. And this behavior can be better seen here. But one of the important findings is what is happening when we calculate the equation of state. So typically when we have non-ideal gases, their description is given by the van der Waals type of equation. So in this case, we will have a term B here, which is basically describing the finite size of molecules, and A is basically describing what is happening with the attraction or repulsion between the molecules. So we take into account interactions as well, and we wanted to see how this will be affected by regularization. So generically for quasi-topological gravity, we showed that this is exactly the equation that we have, the equation of state. And specifically for the Hayward ADS model, we showed that this type of equation of state will diverge for a specific horizon radius r+. And this means that there is only an allowed horizon radius. We can go up to this horizon radius. This is the termination of the physical branch. So in this case, we will have a divergence of the pressure as it's happening exactly at the point where we have the finite size of molecules in van der Waals case. So we have this finite molecular volume, and this is basically connected directly to regularity for the de Sitter core case. For the polymerized case, again, we have a similar equation, and this is because the two frameworks basically have similar reconstruction functions, but it's completely different frameworks. And we have a reduced volume, and we have the positive or negative term here, which is connected to repulsive or attractive forces here for the van der Waals case. And this term here, which is basically the F tilde function that creates these quantum corrections, is shown actually that it's diverging. And the divergence, for example, for the Hayward model is written in this form here. So again, we have this divergence, and for the de Sitter core case only, this is connected to regularity. We show in this paper that for the ADS core, the termination is not because of regularity, but it's because of the sign of this term here. And with this, I would like to summarize. So first of all, I'd like to show you some photos of our groups. So the parts of the works I presented here were done at Macquarie. This was the group we had at Macquarie. And the second part of this talk, where I talked about polymerized case, was basically works here at Westlake University with this group. And the summary is basically that we have different phase structure, interpretation for vacuum and non-vacuum regular black holes. We have different dominant phase transition depending on the dimensionality of the space-time. We have a finite molecular volume that is consequence of regularity for the Sitter core case, but not for ADS. And we have a Hawking page temperature dependence on the regularization core. And with this, I'll end my talk. Thank you.
Okay, thank you for the very nice talk. Now, questions?
Yeah, I think this regular black holes basically just skips the process, the singularity theorem, right? Is this because the matter you can see here somehow doesn't satisfy this classical energy condition or some other reason?
Sorry, can you repeat the question?
So basically, classically speaking, we do have like this singularity because it's
Classically
guaranteed by
speaking,
the
we have the
singularity theorem.
singularity. Yeah. So we need to find ways to actually avoid this type of singularity.
I was thinking like, what's the reason why the singularity theorem doesn't apply here? Is because the matter you introduce doesn't satisfy this energy condition, or?
So this matter will not satisfy the energy conditions.
Okay.
We need to have definitely violation of energy conditions in order to evade singularity theorems. Otherwise, we cannot achieve that.
Yeah, but in that sense, why this is interesting? Because roughly speaking, I can imagine no matter what the metric I write down, I can just put some particular matter in order to force the equation of motion satisfy.
Yeah, you need to find some kind of matter that will force to have these regular solutions that we want. And you can find different matter fields to do that, but one of them is a non-linear electrodynamics.
But is here any like hint why this matter, this particular straight answer should be physical or just some artificial choice?
So typically, just by considering magnetic charge, you do not expect it to be physical because magnetic charge has not been observed in nature. So yeah, based on that alone, I don't think it's a physical matter. So for me, the most physical type of thing is basically the vacuum solutions I described because they're purely gravitational and all the energy conditions are violated just because we have higher order curvature corrections, we can be implemented as like some quantum corrections. And yeah, matter field is not that physical for me.
Thanks.
Typically for ADS case, and so what is a correspond to the interference side? Do you expect some regular black hole correspond to what type of the state or in CFT side or field theory side?
I'm not sure about that. I haven't studied this type of things, so I cannot comment on that.
Also, there are in terms of the phase diagram, for the regular black hole?
In Hawking page transition, there is a direct correspondence with CFT, right? It's strongly coupled to coupled, for example, or it's a confinement and deconfinement transition in CFT for a Hawking page. If you have the small to large phase transition, like we have, for example, in the nonlinear electrodynamics case, then we have, for example, the transition from a high entropic to a low entropic CFT, if that's what you're asking.
But in terms of this standard black hole thermodynamics, so usually you have to define the counter bound, introduce some boundary terms to. So here you.
Yeah, there are different ways to actually study thermodynamics. You can do with a world formalism, or you can use Euclidean path integral formalism, and then that's why you introduce in the Euclidean action the Gibbon-Hawkins term and all the boundary terms to have the. For example, in the magnetic charge case, you need to introduce an additional term to have the charge fixed and provide you with a valid variational principle to do the thermodynamics properly.
So you follow up the same logic to.
Yeah, it's the same one. The only difference is that once you do nonlinear electrodynamics, you have a constraint because, so let me go back. So here, for example, as you can see, you have this magnetic charge. This magnetic charge has a constraint between the mass and the minimal length scale. Once you treat the mass and the length scale as independent variables, then immediately you have a constraint between them. So in this case, if you apply the Euclidean path integral formalism, then you will have an effective temperature arising. But if you consider as fundamental variables this coupling constant A and the magnetic charge, then the temperature will just be the Hawking page temperature, the classical Hawking temperature, the surface gravity. But if you don't do that because of this constraint, you will get an effective temperature. So it depends how you want to do it.
So is there any principle to constrain this ambiguity?
There was a paper recently, I don't remember exactly the authors, they were here in China, and they showed generically what happens when you have this type of constraints for these type of configurations. You have this temperature, the effective temperature arising necessarily if you implement this constraint. So it depends what path you pick, but if we want to be honest, the best choice is to pick the surface gravity to be the temperature, because that's the thing that prevents you from having the conical singularity when you take the metric close to the horizon and you get the Rindler metric, and then you demand these to have the periodicity. This is the only way to actually avoid this conical singularity.
Yeah. Further, when you talk about the phase diagram for free energy, minimize the free energy, usually you can find the critical endpoint from the small tail to be shrunk to a point.
Yeah.
So have you think about this so-called critical clarity of the exponent for such type of this?
Yeah, we calculated for nonlinear electrodynamics only, because the other one, it's not the dominant transition. So for vacuum case, the Hawking-Page transition will be the dominant, so there is no critical point.
Yeah.
But for the case of nonlinear electrodynamics, we studied that and we showed that the mean field exponents are basically what we expect from the mean field theory.
Okay.
So there's no problem with that.
So is it possible to go beyond the mean field?
It's not beyond the mean field theory.
It's not beyond.
Yeah.
If you found
but this analysis was done by using this effective temperature. There have been in the literature where there have been papers in the literature that we used actually the temperature, which is the surface gravity, and they showed that there is some departure to the mean field theory.
Yeah, basically that's also depend on your choice of the temperature.
Yeah. But if you do honestly the Euclidean panthetic formalism, and you can show that you have only the effective temperature.
Yes. Also interesting is it possible to find go beyond the mean field critical behavior? That will be also very interesting.
Yeah. We did that for d equal 9, if I remember correctly, for quasi-topological gravity, because the small to large transition is dominant there. But I don't remember exactly what we found there. I don't think we included it in the paper, but we have done the calculation. I can look and tell you later if you want.
Okay. Any other questions? I mean, actually, I have a comment for this energy momentum violation, because you always, in singularity theorem, because you assume GR, so you have R mu nu equal to T mu nu somehow.
Yeah.
In these things, how to avoid singularity is always to design T mu nu. But the real question is whether this T mu nu can be embedded into some, for example, high derivative gravity, quasi-topological thing, in the sense that you can re-explain them as vacuum solutions. These are different notions, different interpretation, basically.
Sure, yeah. If you consider just matter energy conditions, just the matter.
Yeah,
but in principle, you can shift them to the other side and talk about that. And this shift that you will do, you expect it to violate the conditions, right?
Yeah. But more or less, all the regular nonlinear electrodynamic solutions you show in this picture can be embedded either into quasi-topological or into our high derivative model.
Yeah, so of course. But basically, the regularization here comes up from an infinite expansion of this F, right? Because you can expand this Lagrangian to F.
There are different explanations. You can also embed them as a nonlinear potential for your high derivative terms.
Yeah.
It's always the interpretation issue. And in that case, you can explain them as vacuum. There is no matter field.
Yeah, of course. But the idea is similar with a reconstruction function in quasi-topological. So you just have an infinite summation and you get a function that will regularize it.
Of course, the thing is whether your resummation has what is the convergence radius.
Of course, you need convergence and you need monotonicity for this, for sure,
Yeah, okay, thanks.
Do you know some classes of the regular black hole would violate the weak cosmic censorship conjecture?
They should violate, right?
Yeah, because several years ago, I write a paper and find there are some classes of regular black hole would violate the censorship conjecture. I think it would be interesting to consider more direction for this regular black hole. So I'll send my paper to you if you have interest.
Sorry, can you repeat the last part because I didn't hear that? So
yeah.
you said you studied the
regular
your
black hole
PhD,
before. Yeah.
Regular black holes and weak cosmic censorship, and you found?
And the regular black hole would regular black hole would violate the cosmic censorship conjecture.
Yeah.
Yeah, I think it would be an interesting project, and I will send my previous paper to you if you.
Oh, yeah,
like it.
sure.
Okay, so if no other questions, we thank Ioannis again.
So our next speaker is Zhao, and he will talk to us about an algorithm to generate two-dimensional critical lattice models using competing anion condensation. The floor is yours when this starts showing up your presentation. Yeah, all good.
I think we need to wait. It's a bit slow. But
Yeah, okay.
Yes, it works. Just wait some more.
So, Zhao, the floor is yours.
Yes. So let's start. Today I'll talk about an algorithm to construct critical lattice models, which will very possibly to generate a conformal field theory. Our story can start with reconsidering the famous two-dimensional Ising statistics model. We can review the partition function of the Ising model. That is the sum over of all possible cases of the exponent Hamiltonian. And the critical temperature is 1/2 ln squared 2 plus 1. We can use the Toricode model in the topological order to reconsider this critical temperature. That is, we use lines to separate different spins of the Ising model. And on each line resides on a spin that is a difference between the two spins and separated by this line. For example, if this Si and Sj have the same spin, both spin up or spin down, then on this line we can put a spin up. And if Si and Sj spin differently, then on this line we put a minus spin. And then this will create a tensor product state that on each edge the state is exponent 0 and exponent minus beta 1. And we sum over all we tensor product all edges and sum over all cases. This will result a tensor product omega beta state. And if we take the yes. No. We can put either.
We can put it here.
Yeah, yes.
Not sure where. But do you have your slide?
I can speak without slides. Here? But the line is short. No.
Let's
wait and then send me the slides.
Yeah, you can send slides to him.
Yes. Okay. Yes, some technical problem.
You need to charge.
Yes.
So you can charge on my side.
No, you can also charge there.
Yes.
So do you need some time to charge your
Yeah.
laptop?
Yes, I
Let's
think.
continue.
Yes,
So
I can
you
wait
go
switch.
first?
Go give your talk here. Yeah.
Thank you very much.
So you are ready. 可以吧？Yeah. Oh. I think I saw it.
Is the connection okay?
Not sure. I think it should be this one.
Okay.
So you have HDMI. We can directly connect to HDMI as well.
Yeah. Try.
Okay. Yeah.
Okay. Maybe I just change the.
Or just move your.
Yeah, display setting, I think. It's mirror, it should
Yeah.
be.
And
Okay. Changes.
So our next speaker is Chunhao Guo from Westlake University, and he will talk to us about quantum Monte Carlo probes of entanglement, emergence symmetry, and defect criticality.
Okay.
The floor is yours.
Yeah, so thank you for the introduction, and thanks the Professor Liu to invite us to present our work in the QMI circuit meeting. And I'm Chunhao Guo, the postdoc from Professor Zheng Yan's group, and we are mostly working on to develop computational methods using quantum Monte Carlo method to probe the entanglement, emergence symmetry, and other defect criticality in recent work. So in this talk, I will talk about first how entanglement gives several complementary views of a subsystem. So the entropy, so we start from the entropy and the response. Then we will later see how we cut the system into a bipartite separation and we get the subsystem state. Then we can, from the entanglement structure, we get the entanglement Hamiltonian, and by diagonalize the entanglement Hamiltonian, we can get the level structure, or specifically saying that's the entanglement levels. Then in the end, we can get the effective Hamiltonian of the entanglement and study the spectrum and other more detailed information. So in general, why we study this is these measurements is very difficult in QMC. So first we think about we have two samples ensemble. The first one is our original sample without any entanglement structure. The next one is our target ensemble, which we has the entanglement cut or the bipartition involved. So the problem is, so the problem is the typical overlap could be very small, and there's a rare overlap problem in Monte Carlo sampling. And such difference of the ensemble can be because of the replica gluing or off-diagonal insertion. And when we study the reduced density matrix, that will be the same to choose a subsystem. So to overcome this technical issue, we proposed a method calling the reweighting connect distinct ensembles through nearby ones. So if we think we have two partition functions for different ensemble, we call Z bar and Z. So the technical path is we reweight, or we say reweight annealing from each ensemble. So we are not directly taking the ratio between Z bar and Z. We are first reweight Z bar to a certain point which is known exactly or easy to evaluate. Now we're doing the same thing for Z itself, but along a distinct different path. So schematically, there are three terms. The first term is we reweight to the Z bar. The next is reweight to the Z. And the final one is a bridge. We connect Z and Z bar together at the known exactly point. So practically, in our lattice model of quantum Monte Carlo, we're using a bipartite separation for subsystem A and B. And the A, we have in the subsystem A, the periodic boundary condition of the imaginary time is a loop circle, but in subsystem B, there's an open boundary for the imaginary time. So then we take the replica trick for the replica construction, so we can get the direct information for the Renyi entanglement entropy. So practically, we first study the bipartite revealing annihilation follows a physical coupling path. So we take the example of the dimerized Heisenberg model. We can either take a cornerless bipartition or a corner bipartition. The second one will introduce a possible log term due to a kink in the diagram. So after doing that, when we take each part bipartite calculation, we can collect all the points together along a certain reweighting trajectory, and we can finally get the final annealing run and the full information of the entanglement entropy. So the intermediate points are used for data. So one run maps a broad region to the phase diagram. We can also study the entanglement derivative, which can be understood as a response of the entanglement entropy to the coupling strength. And we can see a very sharp peak at the phase transition or critical point. So that means at the criticality, the peak grows, and we can show a data collapse later that will determine the position of the phase transition GC and the bulk exponent nu. So here we show our recent work for the entanglement entropy in a dimerized Heisenberg model. Well, different cuts, the subleading term is different, but the bulk scaling is the same for all the three different cuts. So that is very unexpected from the previous theory, because if we think the cut is just a measurement setup, that will not affect the universal constant gamma. But the reason is the different cut itself is not guaranteed to be an ordinary cut. It can also carry the gapless, or we see its own defect universality. But the bulk derivative, like that says the bulk critical exponent nu, will be the same for three different cuts. The reason we have been discussed in this paper being the defect criticality nu could be larger than the bulk one. So from the final extrapolation, we will get the bulk information in the end. And to further understand why we eventually get a bulk nu for different Renyi defects, we further study the thermal entropy, not just the entanglement entropy. The thermal entropy can be schematically understood if we rotate the partition function from the integral of the real axis to the integral of the imaginary time. It can be understood as a space-time Casimir effect in the imaginary time axis. And the difference between the two replica, let's say the partition function of beta and n beta, well, gives you some thermal information of the phase transition. So that's our result. We can see the thermal entropy itself can also give very useful information of the criticality and the critical exponent. And here we show the 3 different models of the Wilson-Fisher universality class. And we can see on the left side, it's a sharp peak around the critical point. And the right side, we can do the good data collapse for all 3 different models and get a very stable critical exponent nu for the Wilson-Fisher universality class. And next, we use this method to target on unsolved problem. So for some model with possible deconfined critical point, the transition is weakly first order and very difficult to detect using the conventional method. And we found for a strong first order transition, typically that's a checkerboard JQ model. We can find a very sharp 2-peak structure. And on the right-hand side is more subtle columnar JQ model, which has been still under debate in the condensed matter theory community. Its fate being first order or continuous is not settled yet. But our result shows that it also shows a distinct, very stable 2-peak behavior, and we can only use a very small size to get the stable feature of the first order transition. So that's the one significant strength of this method. And there are some. It can not only study the partition function itself, but can also study the general observables that have been written as a modified partition functions. And this figure shows the exact step we have discussed before. We take 2 distinct Rivet annealing paths and get the final observable. So there are 2 examples. We can study both the Manning particle observable on the left side, and there are some correlation. There are some correlation function observable, and on the right side is a fully non-local disorder operator for the transverse field Ising model. And the Rivet annealing itself can also follow the system size, separation, or imaginary time. It does not have to be the coupling strength. And here we show we're using the same Rivet annealing idea to study the imaginary time correlation function, and we get very consistent results for the benchmark. And as an application, after we get the imaginary time correlation, we can get the entanglement spectrum in the momentum space. And this figure shows 2 examples. The left side is diagonal correlation. The right side is the off-diagonal correlation. And we can see the off-diagonal correlation has a sharper peak age, and that's they are very different from the diagonal correlation spectrum, and that's also consistent with our analysis for the different correlation spectrum. And we can also use this to directly study the reduced density matrix, and using the same method to get the entanglement spectrum by diagonalize the entanglement Hamiltonian itself. And a very useful study is we can get the lower line entanglement spectrum levels and found that consistent with the Tauer state in a spontaneous symmetry breaking phase. And as a very important application, we will study the system with proposed emergent symmetry. And we also introduce an effective temperature that will cooling, if that effective temperature cooling down to 0 using the our developed reverse annealing method, it will goes from the actual entanglement Hamiltonian at t equal to 1 to the fully symmetry channel separated symmetry breaking case. And in that case, we can, since that entanglement spectrum already separate different symmetry channel, that can, using the group theory and Young diagram, the slope of the low-lying states of the entanglement spectrum will give you direct information of what type of symmetry is emerged. The final work we study is at different entanglement cut, we can directly detect the Rayleigh defect it carries on. So on the right-hand side, we study 2 different cuts for the emerged symmetry model we study, and we found on the left-hand side is a 2 original cut. The top panel is you actually cut the system with a physical boundary. The lower panel is doing a virtual entanglement cut. So we see the actual on the upper panel and the bottom panel, the actual cut spectrum and the virtual cut entanglement spectrum is very similar, and that's actually been a very famous conjecture called the Li-Hao-Dan conjecture, been seen that the entanglement spectrum will contain the similar or even the identical information of the physical boundary. And on the right-hand side is a very different cut. We call it tilted cut. Like you tilt the system to 45 degrees and do a horizontal cut. So that one, obviously, it carries a very clean gapless mode and being very different from the ordinary cut. And that directly supports our result that the certain cut, we call it extraordinary cut, will contain the gapless surface sector due to the introduce of the Rayleigh defect. And in our recent work, we also study the Rayleigh defect phase transition when the possible phase transition when we increase the replica number n. We found that for the ordinary and the special cut on the figure A and B, there's almost a parallel or crossover behavior for the twisted Binder ratio. But for the extraordinary cuts of the panel C, we found a very likely phase transition between the n equal to 3 to 4, and this signaling a transition due to the introduce of the gapless Rayleigh defect. But the nature of such phase transition is fully unknown and not being reported in previous study based on our best knowledge. So the nature of such kind of transition is still need further study. Yeah, and that's all of my talk, and thank you for your attention.
So could you go back to you define the critical exponent?
Critical exponent.
Here you define some mu and.
Yeah. So yeah, maybe in this page.
Yeah, but how do you identify the class universality? Which type of the universality?
Like for this study, we are studying O3 Wilson-Fisher universality class.
I see.
Like typically, we are studying something like a dimerized Heisenberg model in a 2D SU2 spin lattice. And the theoretical value, this nu is corresponding to that is the anonymous dimension of the delta epsilon, I believe. And Z1 theoretical value is about 0.71 for the O3 Wilson-Fisher universality class. So that is the anonymous dimension. So when you tune the coupling from the SSB null phase to the paramagnetic dimer phase, so that's a nu we get at the critical point JC of this phase transition.
I see. So this phase transition is fourth order or?
That is a very standard continuous
Continuous
second order phase
crossover.
transition. Yeah.
I see.
And that will host CFT at that point.
I see. So which operator, the scaling dimension of the which operator?
You mean the scaling dimension?
Yeah. You study the autonomous dimension, which is the autonomous dimension correspond to the which operator?
You mean the orbit in CFT? Or?
Yeah, in CFT.
Oh, okay. So actually, I'm not very familiar with the detailed CFT theory yet. So that's mostly numerical result. And usually we just like numerically data collapse a value of a critical exponent of nu. And if that matches the literature result of the CFT, it's mostly from the conformal bootstrap. And we will see that consistent of a continuous phase.
So in numerical result is consistent with analytic kind of. So have you checked all type of the operator? This is a minimum model of or some type of this, what type of this model correspond to?
Oh, that is a dimerized Heisenberg model.
Like, I mean CFT side.
In the CFT side, it's CFT side, what model?
So there are finite number of
this. I think that should be I think that usually we just think it's one sector of the 05 Wilson-Fisher universality class.
I see. So have you checked all type of this operator, all anonymous dimension for all the operator? Have you checked?
There's another anonymous dimension we call the eta, and that's from the scaling of the magnetic field. And that like theoretical value is 0.0375. And that for example, if we just measure the magnetization m square at the JC, and that scaling will give you another anonymous dimension eta.
Yeah. Okay. Okay, thanks.
Are there any more questions?
I mean, probably I missed some parts. So basically, so you find the critical point without scaling up your system, right? Without, I mean, you don't need to go to the thermodynamic limit in the things.
Oh yeah. So like all our result, you can see a finite size calculation.
Yeah, exactly.
And when we see the critical exponent is what is after the extrapolation.
Okay,
Yeah.
I see.
So we do a properly fit of the finite size data and extrapolate.
Yeah. So may I ask how large you need your system to be?
It actually depends on your model. Some models, the finite size effect is smaller.
Yeah.
For example, this one, the 03 Wilson-Fisher is cleaner.
Yeah.
Usually we need, my experience is around, for 2D, it's around 60 times 60 or 80 times 80, we can get pretty good results. But for some more finite size effect, heavy model like the JQ model, like Stanwyck studies is like up to 500 times 500, but the result is still bad.
Okay.
Yeah.
And how many reweighting? I mean, how many different setups do you have usually? Because you use reweighting basically.
Oh yeah. I think the reweighting, like we don't have a specific number of steps.
Okay.
But we do some error control, of course. Like for example, in like mathematically, the reweight step should be infinitesimally small.
Yeah.
But technically, we cannot do that. We can only choose a finite length of the step. But Usually, my experience is if we, for example, we reweight J from 1 to 0, and usually in our productive run, we will take more than 1,000 points. And in this figure, we just show part of the points, as a final published paper.
Okay, thanks.
Any more questions? So let's thank the speaker.
All right, thank you.
So next speaker is Zhao from Westlake University, and he will talk to us about an algorithm to generate two-dimensional critical lattice models using competing anion condensation. The floor is yours.
Yes, thanks for Professor Liu's invitation, and I'm sorry for the interruption. And I will speed up. Yes, just consider the IC statistics model. We construct a tensor product state that it tends to spin up and tends not to spin down. And we take the overlap between this tensor product state and the toric ground state psi. And we will surprisingly find that the inner product is exactly the partition function of the IC statistics model. And when beta takes 1/2 ln square 2 plus 1, and this state and produce the critical partition function of the IC statistics model by overlapping with the toric ground state. So we say this state is the critical state describing the information of the critical phenomenon of the IC statistics model. And in this case, when beta takes the critical value, this critical state is square 2 plus 1 and 1 on each edge. So two questions appears. That one is why this overlap produced the partition function, and then why this state square 2 plus 1 and 1 corresponds to the critical state. The second question is a bit simpler. And we can consider take an arbitrary state that 1 plus R and R. When R equals 0, the state is 1, 0. Iris spin on the A spins up, and this corresponds to an order state. And when R takes infinity, this state corresponds to 1, 1. We normalize it. And this state corresponds to a disorder state or antiferromagnetic state. And when R takes square 2 over 2, then we see that this state is square 2 plus 1 and 1. And this corresponds to the critical IC state. And in the point of view, from the point of view of a toric state, we know in the toric there are 4 anions. That is the trivial anion, charge on E, flux on M, and the dion EM. And the charge on E and the flux on M are both bosons, and they can condense. If we condense the charge, then the new ground state shall be the coherent state, that is the eigenvalue of the creation operator of the charge, which is the Pauli Z operator. So this state, so the coherent state is just the order state that spins up. And we can also condense the fluxon, which is the Pauli X operator. And its coherent state is just the disorder state, that the probability of spin up and the spin down are equal. If we take the sum of this charging condensation state and this fluxon condensation state, we will find immediately the critical state. So we mean that the equal weight sum of the two anion condensation states results in the critical state. Why? Because the charging and the fluxon in the toric case, they cannot braid mutually with each other. The braiding of the charging and the fluxon will produce a minus one psi. So charging and the fluxon cannot simultaneously condense. If you want to condense charging, then the condensation of the fluxon will be forbidden. And if you want to condense the fluxon, then you cannot condense the charging. But if you force to condense charging and the fluxon at the same time, then their condensation will compete, and no one can finally true condense. And so the topological invariance will be broken, and this corresponds to the critical point. So the sum weight sum over, if we sum over omega e and omega n with the sum weight, then the condensation will be completely forbidden, and a new critical point appears. This corresponds to the competing condensation-induced critical state. That is our square 2 plus 1 and 1. The first question corresponds to a very famous principle, that is the topological holography principle. That is studied a lot in recent years. This means that the symmetry of d-dimensional quantum field theory can be regarded as controlled by the d plus 1 dimensional topological order, where the quantum field theory is defined on the boundary of the topological order. And our overlap is just one realization of this principle. That is called a strange correlator. That means that the overlap between the ground state of the topological order and the quantum field theory state on the boundary is exactly the partition function or path integral of the quantum field theory on the boundary. And at the critical point, it could be a gapless state or a gapless state. If it is a gap state, then it corresponds to a symmetry protected topological state. For example, we condense the charging and condense the fluxon, which results in the order state and the disorder state. And it could also be a gapless state. That is one example is our critical state. That is square 2 plus 1 and 1. So the last question is how to design the gapless omega so that it corresponds to the critical state. The idea is our previous anion competing. First, let's briefly introduce what is anion condensation. I will not introduce this, but after anion condensation, the new ground state is controlled by a Frobenius algebra of the fusion category of a spring-net model. It's hard to introduce what is the Frobenius algebra, but simply it can be regarded as a tensor matrix product state. That on each vertex there we give a weight related to related to the three edges linked to this edge to this vertex. For example, if on this edge it links the three labels ABC, MCD, then we give a weight FMCD to this state. And the whole state is the product of all F on all edges, and we sum all possible cases. The condition that an algebra should satisfy is that this move will be naturally an association. We know that usually in the category, this move will require a 6J symbol to relating these two diagrams. But the F symbol cancels this 6J symbol, and this becomes a true associativity. So this corresponds, in this case, we call it is the algebra. And given the input fusion category, we can compute how many algebras it has. And each algebra corresponds to a symmetry protected state. For example, if we input the Eisen fusion category 1 plus sigma, we will find that there are two different algebras. One is the trivial algebra, And another is a non-trivial algebra, consists of two objects, one of psi. We perform the Z2 algebra. And this algebra will produce the normalized symmetry protected state. For each algebra AI, it produces an AI state, and for each algebra AJ, it produces an AJ state. And the critical state, we can learn that it is just the equal weight sum of these two SPT states. And this simple rule will produce the critical omega. And then, if we take the overlap between this critical omega and the apparent straightness ground state of psi, we will produce the partition function of this quantum field theory, and it corresponds to the critical field theory between the phase transition from AI to AJ or from AJ to AI. And from this partition function, we can easily analyze its physical properties. For example, whether it fits the conformal field theory and the critical exponents and or other informations. Yes. This is an analyze to a method to numerically compute the central charge of the critical state. We can take the renormalization group flow and infinitely contrast this plaquets. And for each four plaquets, for each square plaquet, when we contrast it, it will result in unit cell of our system. And if we continue this contraction, we will find that the renormalization, the state will flow to a fixed point, and a fixed point of the transfer matrix, and the eigenvalues of this transfer matrix will tell us many information of the critical conformal field theory. For example, the conformal dimensions of the primary fields and the central charge. If the central charge is 0, then it corresponds to a first-order phase transition. If the central charge is non-zero, then it corresponds to a conformal field theory. And using this method, we can compute the central charge of the conformal field theory, and it will tell us that what conformal field theory we will get. And this method can also be applied to the computation of 3 different anion condensations. We introduced 3 different Frobenius algebras and SPT states, A1, A2, and A3. And we take the critical state between A2 and A3. Yes, A2 and A0. And we use A3 to pull this state from the critical point to the tricritical point. But one problem is that the A3 will have different overlap with A1 and A2. So if we want to correctly compute the critical line, we must take a Schmidt-Nodal orthogonalization. And after this method, we will pull a critical line between the A2 and the A0 SPD states from the critical point to the A3 state. And we can also pull the critical line between A2 and A3 state and A0 and A3 state. And these 3 lines meet the 3 critical points. This is, yes, I have erased it. Let's consider some examples. For example, if we input the Zn group, then the Zn group at least have 2 different Frobenius algebras. In this case, it is just subgroups. One is a trivial subgroup, and the other is a full subgroup, the Zn itself. And the critical will naturally generate the n-pose model. For Z2, it creates anything. For Z3, it creates 3 poles, and for Z4, it may create 4 poles. And when n is larger than 5, we will find that C is almost 0. And this corresponds to a first-order phase transition, as we know. And the n-pose model for n larger than 4 corresponds to a first-order phase transition. The other case is the SU2 level K model. This will produce the well-known RSOS conformal field theory. And the benefit of our method is that we have classified topological orders and know it very much, but we have less knowledge about conformal field theories. So if we input a very complicated but still controllable topological order, it will produce very complicated conformal field theories that may have not been observed before. Yes, this is the A5 case, the competing of 3 different phases. Yes, this is our novel examples that we input a very complicated topological order that we call it Haar graph. And the competing of this Haar graph will generate many new safeties that have never been reported before. For example, in this case, 0.8 perhaps is perhaps the 3-IC model. And this 1.3 is a novel conformist theory that have not been reported in literature before. And also this 2.1. Yes, in this case, this 2.1 and this 1.3 are all new conformal field theories that we have not known before. But now, using our method, we can start from a topological order and take the onion computation to break the topological invariance and result in new conformal field theories. Yes, that's our conclusion, that we produce such a method to start from the topological order and take its competing onion condensation to produce a conformal field theory. In most cases, it is always a critical lattice model. But if we are lucky, then we will find that this critical set is the second order, and it corresponds to a conformal field theory. And using this method, we indeed find new conformal field theories that have not been found before. And yes, that's the talk of me today.
Are there any questions?
So what do you mean by the higher dimensional critical lattice model? You introduced a more higher layer?
Yes. I think this method can be applied to very general cases. For example, the condensation of 3+1D topological orders. And it will produce 2+, for example, 2+1D conformal field theories.
So you can talk about the 2+1 or higher dimensional safety?
Yes.
I see. How about all this model is quite minimal, so is it possible to extend to irrational case? Irrational model, for example, Liu field theory, etc.
In fact, in many cases, it is not a minimal model. For example, our Haar graph, it is.
Yeah, but it's rational model, right? But how about the irrational model? Because the spectrum is continuous, and it's hard. I guess it's hard to generalize.
Up to now, we have no idea how to generate irrational models.
And further, have you talked about the IC model, tensor product IC model, and I saw there is a model you talk about the IC model plus tensor product, some other.
That's a possible direction. We are talking about just the IC model.
I see. Okay.
I mean, this is always a thing related to this rational and irrational, because here you always use a fission category, right?
Yes.
And I mean, that's why probably you always get rational safety.
Yes.
And the thing is now you need to turn to a irrational, I mean, not a fission category like Liu-vertical FT or, on the lattice, of course. I don't know,
We started with a very a topological order, so it is always related to a fusion category. if we do not start with the topological order, we even does not know how to take the phase transition of this model. Then it will be harder to generate the competing of any conditions.
But then from the correspondence, it's hard to generate irrational CFT, right? Because, I mean, here you also have the mapping between the fusion category and the fusion rules in CFT, right?
Yes.
So, yeah. Okay.
Any more questions?
I mean, this is maybe continue. This is always correspondence between topological theory in the back and some boundary triangulation and a continuum limit on the boundary gives you different. Yeah.
Yes.
Yeah. Yeah, because I mean, if it's really ADS CFT, it means in the back you have irrational. It's not a fusion category because of the gauge, because of the symmetry group.
Yes.
Which is not in this case.
Yes.
Yeah, this is more general holographic. I mean, or RTR.
Yes.
Yeah, oxim. Yeah.
I have a question about how to map this topological phase, and I'm wondering. I'm curious about how to map to the topological phase. And you see that the typical fusion rule and typical topological.
In fact, the input fusion category of the in the block corresponds to the symmetry generators of the lattice model on the boundary.
Could you show some picture or maybe?
Yes, I want to paste some. Yes, I have. For example, we know that a minor sign corresponds to the difference between spin up and spin down. Okay. I can take back to this page. Yes, we still start with the IC model. A minor line corresponds to the difference between spin up and spin down. And if we move this line downwards, we will flip this minus sign to this plus sign. So you can imagine that if we scan this minus line from the top infinity to the down infinity, then the spins of the whole Ising spin system flips. So this minus line corresponds to the G2 flipping symmetry of the Ising model. Mm-hmm. And another example is the Ising case. We know a sigma line. In the Ising model corresponds to the EM exchange defect. When the E charger crosses the sigma line, then it will transform to a fluxon. So if you scan this sigma line, then the charging will all flip to the fluxon. And we know that this the charging condensation corresponds to the order state, and the fluxon condensation corresponds to disorder state. So this charging fluxon exchange just is the Kramer-Wiener duality in the Ising case.
I see.
So
you can realize the KS duality
yes.
in the spin chain model.
Yes. This is how the fusion rule enters.
If there are no more questions, we should thank the speaker once again.
Thank you very much.
Yeah. So this RQI circuit has come to an end. Let's thank all the speakers once again and all people that were here. Special thanks to Rick for making this possible, and yeah, come and say the final words.
Thank you, Ioannis. All right, so just to end the circuit here. So again, let's thank the organizers, Ioannis and Professor Liu, for organizing this and for hosting me here for the week. So thank you so much. This was very good to see all the research being done here. From quantum gravity to condensed matter, the relationship between everything. It was very nice to see everything. So we will have, this was the penultimate edition of the RQI Circuit, in person at least. Next week we'll be in Hanover. We'll hear about some quantum field theory, entanglement in quantum field theory, and other interesting related topics. So it will start at 10 a.m. local time in Hanover, so 4 p.m. for you guys. So if you want to watch it on YouTube, it will be live there. So feel free to join there. And yeah, for whoever is watching online, time zones will go back to more European friendly, I would say, next week. But yes, so next time we're going to go to Hanover, and I hope to see you all there, or that you all can enjoy that, and whoever is watching online too. So thank you so much.